Hello everyone. If you want to learn binary search from the scratch, this is the perfect video for you. In this 3-hour Snyder cut, we will explain you what is binary search, intuition behind binary search, the code and the time complexity. After that, we'll jump into problems. First set of problems, given a sorted array, apply binary search. Second set of problems, array is not sorted, but you still have to apply binary search. Third set of problems, nothing is given. You have to build your own search space and then apply binary search. Finally, under which scenarios we can apply binary search. All these things will be covered in this 3-hour Snyder cut. So watch, learn, have fun. Thank you.
So hello everyone. So the topic for today is going to be searching, right? So we are going to look at different searching algorithms. We will start with linear search, and then we will move on to binary search. We will look at ternary search, and we will solve some problems related to binary search. Okay. Now, as always, after the class, we will have an assignment for you guys. So after every class, you are given an assignment so that you can actually apply what you have learned in the class and solve problems so that you can solidify the concepts. The link for the problem set will be in the video description. Apart from that, there will also be a link for a chat forum so that you can talk to your peers and discuss any issues that you face while solving problems. So that is for today. There is one more announcement that I would like to make, which is that a lot of students come to us and they say that, hey, I need help with interviewing, right? So they tell us that they somehow get nervous during interviews. And a lot of students say that when I'm doing competitive coding online, I am able to solve problems. But when I'm in a face-to-face interview, I somehow get nervous, or I'm not sure what the correct approach or what correct approach should I take while solving the problem in an interview. So to handle that, we have organized a mock interview for you guys today, right? So suppose that you wanted to see how an ICPC World finalist, right, someone who is very strong at data structures and algorithms, how such a person would behave, would approach a problem in a Google interview. All right, without further ado, let us dive into today's lecture. So let me just share my screen. All right, I hope that this is visible to everyone. Can someone just confirm these? Perfect. All right, let's begin. So I assume that most of you would be familiar with some sort of searching, right? Suppose that you have a collection. Suppose that you have a haystack. And you are looking for something in this haystack, right? Suppose a needle. Then how do you usually search? Well, the way we usually search is we pick each item one by one. Pick each item one by one. One by one. And we inspect it. Right? We see if this is the correct item, if this is the item that we are looking for. Now, this can be very, very time consuming, right? So just to prove this point, let us play a very simple game. Okay. So I want you all to play this game. So I have a number in my mind, right? And I'm telling you that the number is between 0 to 1000. Okay. Now, what you're supposed to do is you're supposed to guess what the number in my mind is. I'm not telling you the number right away. So you're supposed to make guesses between 0 and 1000. So if you could please start spamming in the chat, just tell me your guesses in the chat. And whenever I see the number that I'm guessing, that is in my mind, I'll let you guys know. All right, so can you guys please start? I have a number between 0 to 1000 in my mind, and you have to guess that number. So start pasting in the chat. What do you think the number is? You have no other information. 786, not really. That is not what I had in my mind. Okay, I got 52, 30, 91, 900, 100, 99. No, none of those. A lot of zeros, some 500, some 304, 300, 666, 120, 76, 2. None of these. 50, no, 3, 404. 545. None of these. None of these. Please give some hint. So Tushar has a very important thing over here. Tushar says, if you could give us some hint, then we will be able to approach that particular solution much faster, perhaps. Right? So we see that if you have no information, right? If you have no information about how to search, then your best chance is to randomly check, randomly guess, right? Or if you don't want to randomly guess, your best chance is to basically check each possibility, right? So it could happen that first you say that, okay, you are guessing the number 1, then you move on to number 2, then you move on to number 3, and you keep doing that, you keep making guesses till I say that, yes, your guess is correct, right? So this is an example of something called linear search. Why linear? Why linear? Because you are going over each item linearly, right? Basically, you're going over each item once. So this is called linear search. And let us suppose that you have n elements, and you're looking for some value. Right? You're looking for some key in this set of n elements. Then how much time will linear search take us? So what is the time complexity of linear search? It is order of n time, right? And while we are at it, let us also quickly discuss the space complexity. So how much space does it take to do a linear search? Well, this is just order of 1, right? Because we don't really have to store a lot of memory. We can just use a couple of temporary variables and perform the linear search. All right. So I assume that everyone is familiar with this linear search. So linear search is very inefficient. Now the question comes, can we search faster? Can we search faster? Right? What do you think the answer to this is? So this is the question. Now I'm asking you, what do you think the answer will be? Now, as most things in life, the answer is it depends, right? It depends. Well, it depends on what? It depends on, is there some pattern in the data that we can exploit, right? If we have some pattern in the data that we can exploit, then perhaps we could search faster. Does that make sense? For example, let us play this game once again. Right? Let us play this game once again. I am going to guess, I'm going to have a number from 0 to 1000 in my mind. And you are supposed to guess that number once again. However, this time, whenever you make a guess, I'm going to tell you if your guess is too high or if your guess is too low. All right? Cool. So let us begin once again. I have a number in my mind. And could you start guessing, please? So Mudasir says 2. Well, 2 is too low. Then Mudasir has guessed 34. 34 is too low, once again. Then the next guess is 123. It is too low. The next guess is 233. That is too high. Sahil says 500. That is too high. All right. Keep them coming. Keep the guesses coming. The next guess is 150. This is too high. Then what is your next guess going to be? So 188. No, 188 is still too high. 200 is still too high. 10 is way too low. Yes. So 130. 130 is too low. And then what do we have? All right. So 130 is too low. Can you make more guesses now? 143, right? Someone guessed 143, and that is exactly the value that I was thinking of, right? This was my guess. This is correct. All right. So we see it took us some time, right? It took us some time. It was not that we were able to guess the answer immediately. However, we were able to hone in on the answer, right? So you know of homing missiles, right? The homing missile doesn't really know where the target is, but as it moves forward, it will get closer and closer to the target. Right? That is what we were able to. We were able to home in, right? Home in on the answer. Why were we able to do that? Because there was some pattern in the data that we could exploit. The pattern was that we were able to figure out whether our guess was too low or whether our guess was too high. Right? Now, a lot of students think they have this misconception that some sort of a binary search, right? Binary search can only be applied when the data is sorted. And that is not the case. The data need not be perfectly sorted for you to be able to apply binary search, right? So what we are looking for in the data is we are looking for some pattern or some sort of ordering. Okay, so let us define some nomenclature over here. Let us define some theoretical nomenclature over here so that we can make concrete progress over what binary search is. All right. So suppose that you have some search space. And let us represent the search space like this. In the search space, this search space is basically a set of possibilities, of possible answers, right? So there's one answer possible over here. So this is another possible answer. This is another possible answer. Another possible answer, perhaps another possible answer, and so on. What binary search says is that when you make a guess, let us suppose that you made this as the guess. When you make a guess, if you are able to eliminate a large fraction of your search space, then you can search efficiently. If this is the case, then you can search efficiently, right? Let's see how. So let us look at the previous game that we played. In the previous game, whenever you came up with an answer, right? Let us say that you came up with an answer that, hey, the guess is 200. Then all I told you was whether the guess was correct or not, right? All I told you was whether the guess was correct or not. And that basically allowed you to eliminate this possibility itself, right? So you made a guess 200. I told you it is not correct. So you can eliminate this possibility. Can you eliminate any other number? Did you get information about any other number? You did not. Right? On the other hand, in the second version of the game, suppose you guessed 200 and I told you that it was too high, then you could have eliminated every number. You could have eliminated all these numbers that were greater than 200. And your search space would only remain with the numbers that are less than 200. Right? Does that make sense? Yes. So this is something that we will try to exploit in binary search. So basically, binary search can be applied whenever you can remove, right? Remove or prune a large chunk of your data, of your search space with every guess. All right. Cool. So let us look at a more concrete example of this. So mostly when we are talking about searches, the first thing that would come to our mind is that we have an array. Right? We have an array. Suppose we have an array of integers. Right? This array has multiple values. Let us say that the size of this array of size n. Right? The size of this array is n. And we are supposed to search for a particular value in there. So given an array, what type of things are we able to binary search over? So whenever we try to binary search, we try to come up with a proposition. Does everyone understand what a proposition is? Yes, a proposition is something that takes two values, any of two values, right? A proposition can either be true or it can be false. Right? A proposition can either be true or it can be false. Now, if you can come up with a proposition, such that your array starts looking something like this, that for this particular element, the proposition is true, for this element, the proposition is true, for this element, the proposition is true, and so on. At some point, the proposition starts becoming false, right? If you are able to come up with a proposition that can make your array look like this, then you are able to perform binary search on this array. And what will that binary search give you? That binary search will give you this boundary point. That binary search will give you this point where the proposition flips. All right, is that clear? So we will look at a little more concrete examples of these. Cool. So let us once again go back to this game of guessing the number. Right? Let us suppose that I gave you an array from 0, 1, 2, all the way till 1000. Right? All the way till 1000. And I had a guess. Let us say my guess was this number G. The correct answer was this number G. Now, what is my proposition over here? What is my proposition over here? So what is the proposition that makes sure that everything to the left of G is true and everything to the right of G is false? Can someone tell me that? So what proposition should I make so that every number to the left of G should result in false, while every number to the right of G should return in true? Exactly. So the proposition can be as simple as, is A of I less than G? Right? Is A of I less than equal to G? Right? What happens in that case? So if G is my guess over here, then every value to the left of it, yes, it is less than equal to G. So all these values will be true. On the other hand, on the right hand side, all these values will be false, because they will be, if the array is sorted, all these values will be false because they will be larger than G. So if I'm able to come up with this proposition, then binary search will allow me to find this junction. It will allow me to find this point where the true flips from true to false. Is that clear? All right. And now we have basically come up with the final definition of binary search. Right? Binary search does not require you to have a sorted array. Right? That is a misconception, that you need to have a sorted array to perform binary search. What you really need is, you need this proposition. If for any search space you can come up with such a proposition, then you can apply binary search on that search space, right? Irrespective of whether that search space is sorted or not. All right. Perfect. So let us dive into some more concrete things, and let us try to look at the implementation of binary search. Right. So once again, suppose that we have been given an array, right, of size n, and this array is of integers, right? And we are also given a key, suppose k, that we are looking for. And for now, let us suppose that the array is sorted in ascending order. Right? Then what we have to do is, we have to search the element. We have to find the index of k in this array, if it exists. Right? If it exists in the array, then we are supposed to find the index and return the index. Otherwise, what we're supposed to do is, we're supposed to return the index where k should be inserted. Inserted in the array. Is that clear? Yes, is that clear? So once again, suppose that we have an array that looks like this: 0, 3, 7, 12, 15, 16, 20, right? And I give you the key, let us suppose 12. Right? So in this case, what are you supposed to return? So let me give the index as well. This is 0, 1, 2, 3, 4, 5, 6. So in this case, what are we supposed to return? If this is the array and this is the key, then what value will we return over here? The answer we are supposed to return over here is the index 3, right? Because 12 is at the index 3, right? On the other hand, if I ask you to find the value, let us say k equals to 17, right? If I ask you to find the value k equals to 17, then what are you supposed to return? So there are multiple variants, right? In some cases, I might ask you to return -1 because 17 is not present in this array. I might ask you to return -1, but that is not what we are looking for over here. We are saying that if the value is not present in the array, then tell me the index where that value should be inserted. Right? So if 17 was inserted in this array, then what value, what index should it be inserted at? Should it be inserted at this location? Should it be inserted at this location? No, it should not be, right? Because 16 is less than 17. It should be inserted at 20's position, and 20 should be shifted to the right. Yes, 17. If 17 was inserted, 17 would come in the 6th position, and 20 will be moved to the right. Right? So if the search key is 70, then you are supposed to give me back the answer index equals to 6. Is that clear? Right? So this is the classic problem of binary search. We have been given an array. We have been given an array which is sorted, and we have been given a key, and we have to search this key within the array. Right? Now let us first look at the implementation of how we would do this binary search, and then we will discuss the time complexity, right, and the corresponding analysis. All right. So let us start with this thing. So suppose that we have this function int binary search, right? And in this we are receiving a vector, right? We are receiving a vector. So we can say that, okay, we have an vector AR, vector of int AR, right? Apart from that, we also have the key. So we have an int. So this is not a semicolon, this is a comma. We have an int key. All right. This is the function that we are going to write. Yes, Shubrata, yes, in this case, we are accepting a sorted array. All right. We will come to binary searching over non-sorted arrays in some time. We are starting with the most simple thing, that the array is sorted. All right. Cool. So how would we write this particular piece of code? So when binary searching, there are certain things that we would like to identify. There are certain things that we would like to identify. If we are going to search, then the first thing that we need to identify is our search space, right? Is our search space. Now, if we have an array, then what do you think the search space is going to be? If we have an array, then what is the search space? Well, the search space is all the possible different indexes in the array, right? The value could be at index 0, the value could be at index 1, and so on till the last index. So the search space is the indices of the array. Well, what is the minimum value of that search space and what is the maximum value of that search space? So can we somehow draw a boundary? Can we draw a boundary around that search space? Yes, right? So in this case, the boundary is from 0 all the way till n minus 1, where n is the length of my array. Is that clear? All right. So when I'm defining the boundary, I will encapsulate. I will basically wrap my search space around this within this boundary. So I will say that, okay, let us suppose that we have some low, right, and that is the minimum possible value in my search space, and I also have some high, and that is the maximum possible value in my search space. And I can write over here that n is perhaps n equals to ar.size. All right. Cool. Now that we have the boundary, we are supposed to perform the binary search. Okay. So this was the first step of binary search. The first step of binary search was to bound or to establish the boundary of the search space, right? The second thing Once you have established the boundary, the second thing is to make a guess. To make a guess. So how do we make a guess? Let us suppose that we have some search space and we want to make a guess. What guess do you think we should make? What guess do you think we should make? So we can make any guess, right? We can make any guess. However, we should try to make a guess that allows us to eliminate a very, very large chunk of the search space, right? Does that make sense? So if I have this array, and this is sorted, right? And this is my low, and this is my high, right? If I make this guess, if I make a guess over here, then what will I be able to eliminate? What will I be able to eliminate? I will either be able to eliminate this part, or I will be able to eliminate this part. Yes, I will either be able to eliminate this left half if my guess was too high, right? Or I will be able to eliminate this right half entirely if my guess was too low. Now, what is these values? What are these values over here? What are these values over here? Let us say that this is x, then this will be n minus x, right? Now the question is, in the worst case, right? If I'm very, very unlucky, then my guess will be on this side, right? I will be able to eliminate a smaller value. I will not be lucky. I will not be able to eliminate a very large value, right? So I should try to make it so that x is as large as possible, right? Both x and n minus x are as large as possible, right? So that no matter whether I'm lucky or not, I'm able to eliminate a large chunk of my search space, right? So what guess should we make over here? We should perhaps guess the middle element. We should perhaps be guessing the middle element. Is that clear? Right? So this is the second thing. Once we have decided the search space, once we have the low and the high, now we are supposed to find a mid, right? So we will guess a mid. So we will say int mid equals to low plus high by 2, right? And notice that this is integer division, right? This is integer division. All right, cool. So is this part clear? Is this part clear? That we calculate the mid. All right. Once we have the mid, then what do we do? Once we have the mid, then what do we do? The third step is to check the proposition. Check the proposition and prune, right? And prune our search space. Right? We have to check the proposition and prune our search space. Now, the proposition can be either true or false. Right? The proposition can be either true or false. However, in most of the cases, we can have 3 values. Right? We can have 3 values. Either my guess is too high, or my guess is too low, or my guess is exactly correct. Right? So let us look in this case. Let us look at that in this case. So what possibilities can I have over here? Right? What possibilities can I have over here? If AR of mid is less than the value I'm looking for, is less than the key. If AR of mid is less than the key, then what does that mean? Is my guess too high or is my guess too low? If the location that I'm looking at the location mid. If the element at that location was less than the key, then is my guess too high or is my guess too low? Well, the element was less than the element I was looking for. So I am sure that since the array is sorted, any value that is at AR of, let's say, 0 or AR of mid minus 1, right? Mid minus 1, all these different values are going to be less than the key as well, because the array is sorted. So my guess was too low, right? My guess was too low. So what should we do? We should adjust something, right? We should adjust the search space. How should we adjust the search space? We can say that low equals to mid plus 1, right? Mid plus 1. Right? So basically, earlier This was the search space, this was low, and this was high. Right? I made the guess at mid. And I found out that this guess was too low. Right? This guess was too low. So what should I do? I should shift this low. I should shift this low to the element just right of it. Right? So this element should now be low. And basically by doing that, I am eliminating all these different possibilities. Right? I am eliminating all these different possibilities. Is that clear? So we should move up the low. Is that clear? We should increase the low. All right, so that is one case. So what other cases can we have? Else if AR of mid was greater than key, right? If AR of mid was greater than the value I am looking for, then what happens? Then my guess is too high. And by the same argument, now I need to decrease the high. Right? And now I need to say high equals to mid minus 1. Right? Otherwise, if even that is not the case, then what possibility remains? If it is neither too high, if it is neither too high nor too low, then what possibility remains? Then it must be exactly correct. Right? Else my guess was exactly right. Right? I guessed the perfect answer. So in that case, I can just return the index. Right? Because I looked at this particular index, AR of mid, I looked at this particular index and I found a value that was exactly equal to the key. Right? It was neither greater than key, it was not less than key, so it must be exactly equal to the key. So I can just return this index because this is the index that I am looking for. Is that clear? Yes? Perfect. Now let us look at the code that we have and let us see if there is something missing over here. Right? Let us see if there is something missing over here. So once again, in the code, what we are doing is we are saying, let us initialize a search space. Initialize space, right? Then we make a guess. So this is our guess. And based on the guess, we adjust the search space. So will we be able to, after one adjustment, will we be able to reach the answer? Will we be able to reach the answer after just one adjustment? No. Right? We have to continuously adjust our guess. Right? So we have to do this entire thing again and again. We have to repeat this. Right? We have to repeat this entire thing. So how should we repeat this entire thing? Let us put it inside a loop. So let me add some space over here. And let me say, I will loop. Let us say I loop forever, right? While some condition. So I don't really know what this condition is, but as long as this condition is true, I will keep looping. Right? I will keep looping till this condition is true. Is that clear? Right? So we could have done several things over here. We could have called this function recursively as well. Right? Based on the adjusted guess, we could have called this function recursively as well. But recursion will have a lot of different issues with itself. So it will use a lot of memory because it will use the recursion stack. So let us not do that. Let us go with the iterative approach. Right? So once we have made a guess, and we check the guess, after we check the guess, we will adjust our search space. Right? Now, once we have adjusted the search space, what do we have to do again? We have to make the guess again. Right? We have to make the guess again and again. But till what time should we continue this? Till what time should we continue this? Should we continue this forever and ever? Should we continue this forever and ever? No, we should only continue this as long as our search space has elements in it. Right? If our search space has elements in it. So basically, if our search space is empty, then it does not make sense to keep looking inside that search space. Right? If our search space is empty already, then it does not make sense to keep looking inside that search space. So when will our search space be empty? Right? When will our search space be empty? Let us suppose that this is my array. This is the low and this is the high. At what point would I say, for what values of low and high would I say that my search space, that this particular area, this particular range over here, this is empty? When will I say that? What happens when low equals to high? When low and high are the same. What happens when low and high are the same? Well, then my search space is not empty. Then my search space has one element, which is a of low. Right? If low equals to high, then my search space has one element, which is a of low. So when will my search space be empty? When low will be greater than high. Yes. As soon as this happens, as soon as this is my low and this is my high, right? Then I'm saying that the search space is everything that starts from low and goes till high. Well, it cannot go till high, right? My search space is empty now. Is that clear? So I am supposed to continue this loop till my search space is not empty, right? So what will be the opposite condition over here? What will be the opposite condition over here? So if this tells me that the search space is empty, then how do I check if the search space is not empty? I will check it by saying while low is less than or equal to high. Is that clear? Yes? Right? And this is very important. Right? If you miss this equal to, you might get an incorrect answer. Right? Or if you do something else, you might run into an infinite loop. So it is very crucial that we have this condition right, because this condition tells us when to terminate. It tells us when our search space is empty. Okay? And I mean, a lot of the times people are worried that, okay, I don't really know how to determine what condition should go over here. So here's the trick once again. To determine what condition should go over here, you have to ask yourself, when will my search space be empty? When will my space be empty? Right? And based on that, you will be able to come up with a condition. All right? Cool. So this is basically the code of binary search. We started with a search space. Repeatedly, while the search space was not empty, we made a guess and we adjusted that guess. Right? If our guess was perfect, we simply returned that guess. But what if we did not find that element? What will happen then? What if we did not find that element at all? What will happen then? Well, then we will keep on looping. We will keep on looping till the point our search space becomes empty. Right? Till the point our search space becomes empty. So what will happen is we will not be able to return over here. However, we will come out of this while loop. Right? So we will come out of this while loop. We will be over here at this point. And what values of low and high will we have? We will have a value such that low will be equal to high plus 1. Right? That is when our search ends. Right? And what is this location? Can you tell me what this location is? This location is exactly the location where I should insert this element. If I were to insert this element, this is exactly the location where I should insert this element. So when I am at this point, just give me a second. When I am at this point, I know two things. The first thing I know is that low is the index. Is the index where I should insert it. Where I should insert key. If I was going to insert it, then low is the location where I should insert it. Second thing I know is key was not found in my array. Key was not present in my array. Right? Is that clear? Now, once again, if we were to simply find the index of the, if we were supposed to find the index of the key and return -1, if the key was not present, then over here we will return -1. Right? Then over here we will return -1. Right? On the other hand, more practically, whenever you see a library implementation, we don't usually return -1. Instead, we return the index where I should have inserted the key. Right? So over here we can also return the low. Return the low value, right? Because this is the location where I should have inserted the key. Is that clear, guys? Yes. Now, one common question is, if you are returning -1, then your caller knows that the element was not present, right? Because hey, index cannot be -1. Index of a particular value in an array cannot be -1. Indexes start from 0, right? So in this case, my caller knows that the element was not present. But what if I return low? What if I, instead of returning -1, what if I return low? How will the caller find out if the element was present or not? Yes, the caller has to be able to make that distinction, whether the element was present or not. So how will the caller get to do that? Well, the caller can check. The caller can simply check. So it will say that, okay, index equals to binary search, the array and the key, right? And the person can check, the caller can check if AR of index equals to key, right? If AR of index equals to key, then we found the key, right? Then we found key at index, right? Otherwise, it means that we did not find the key, but this index is the location at which we are going to insert it. If we were to insert it, so we can say did not find the key, but if we were to insert it, it should be inserted at index. Is that clear? So the caller will have to make this additional check. Is that clear, guys? Yes? Okay. So Rohit has a question over here. Rohit says, what should we return? What should we return if key is less than AR of 0? Right? That's a very good question. So suppose that we have this array. This is the index 0, this is the index 1, and so on. Right? Let us say this value is 10, this value is 11, this value is 12. And let us say my key was 9. Right? Or let us say my key was 5. So first of all, is my key in the array? Is my key in the array? No, it is not in the array, right? Not present. Not present. If I were to insert this value, where should this key go? If I were to insert this value in the array, where should this key go? Can the key go at location -1? No, right? There is no index -1 in the array. So where should this key go? This key should go at index 0. The 5 should be inserted over here, and everything in the array should be shifted to the right. Right? Shifted 1 to the right. Does that make sense? So over here, our binary search, when I search for key equals to 5, my binary search should return the value 0, right? It should return the index 0. And that is exactly what our code will do. All right, that is exactly what our code will do. Is that clear? Okay. So let us move on. So I hope that the code and the implementation of binary search is clear to everyone. Now let us look at some improvements that we can make on our code. So one of the most important improvements is that we never try to calculate. We never try to calculate the mid like this, right? And you might have seen this a lot of times. People do the following. People instead of saying int mid equals to low plus high by 2, right? They do something else. They say int mid equals to low plus high minus low plus high minus low by 2, right? So can someone tell me the difference between these two? Can someone tell me the difference between these two? Why do some people do it this way? Why do some people do it this way? Well, let us try to look at the mathematics. Right? Let us try to look at it mathematically. So if I have low plus high by 2, right? This is one thing. On the other hand, I can have low plus high minus low by 2. And let us see that if there is a difference between these two. So what I can do is I can take the denominator 2 common over here. So what will happen? The numerator, this will become 2l plus h minus l. Right? This will become 2l plus h minus l. What is that? That is simply so one l will cancel out. This will simply be low plus h. Right? This will simply be low plus h. So we see that the left hand side and the right hand side are equivalent. Right? From a mathematical point of view, they are equivalent. So what really gives? Why do people do this? This is more complicated, right? The reason why people do this is, even though they are mathematically equivalent, when we are dealing with computers, we can run into an overflow, right? When we are doing addition, we can run into an overflow. For example, let us suppose that our integer can only store. So let's suppose that the largest value our integer can store is, let us say, 10 to the power 9. right? Let's say 1 billion. Okay, let us say that our low is 5 into 10 to the power 8. Okay, so our low is 500,000. Let us say that our high is 8 into 10 to the power 8, right, which is 800,000. Right? If I have something like this, what will happen when I try to calculate the mid? What will happen when I try to calculate the mid? I will be doing 5 into 10 to the power 8 plus 8 into 10 to the power 8, right? This will be low plus high, and then I will divide it by 2. Yes, then I will divide it by 2. But what will happen over here? When I try to add these values, this will be 13 times 10 to the power 8. Right? And we just saw that 13 into 10 to the power 8, this cannot fit in my integer. My integer can only be up till 10 to the power 9. This is greater than 10 to the power 9. Right? This is what? This is 1.3 times 10 to the power 9. Right? So this value over here, this will overflow. This will overflow. And the value that I will get over here will be garbage. Right? It will give me a wrong answer. And then I divide the wrong answer by 2, I will eventually get a wrong value of mid. Is that clear? Yes. On the other hand, if I do it the other way, if I say low plus high minus low by 2, right? If I do it this way, then what happens? Then this will be 5 into 10 to the power 8 plus 8 into 10 to the power 8 minus 5 into 10 to the power 8 by 2, right? And is this operation going to overflow? No, I'm subtracting things, right? I'm subtracting things. So the answer over here will be less, right? The answer over here will be less than this value. Yes. So what do I get over here? I get 5 into 10 to the power 8 plus 3 into 10 to the power 8 by 2, right? And then then this will give me the correct answer, 6.5 into 10 to the power 8. Is that clear? This will not overflow. Whereas this approach will overflow. Is that clear? This approach will overflow. All right. So Amit over here says that, hey, we can just use a different data type, right? If we are dealing with an integer, maybe we can switch to a long data type, right? But I mean, what if you were using a long, right? Amit, the problem is, what if you were using a long? What would you do then? So in general, it is a good idea to implement the mid calculation via this particular approach. Okay. All right. So that is the improvement we are going to make over here very quickly. We are going to go to a code of binary search. We are going to remove this and we are going to improve it. We are going to say int mid equals to low plus high minus low by 2. All right. Perfect. Okay. I hope that everything is clear till now. Now let us try to analyze the time complexity of binary search. All right. Let us try to analyze the time complexity of binary search. Time complexity. All right. So how do we talk about the time complexity of binary search? So what is really happening is, initially I have the search space of size n. Right? Initially I have the search space of size n, and I guess the midpoint. Right, as my guess. Right? If my guess is too low, then I'm able to remove these elements. Right? I'm able to remove these elements. How many elements was I able to remove? So if this is 0, this is mid, and this is n, then after one guess, if my guess was too low, then how many elements was I able to remove? I was able to remove n plus 1 by 2 elements. Right? Yes or no? On the other hand, if my guess was too small, then I would be able to remove all these different elements. Right? Everything from mid all the way till n minus 1. Right? Even then, I was able to remove n plus 1 by 2 elements. Right? I was able to remove n plus 1 by 2 elements. So what really happens is, every time I make a guess, I'm reducing the search space by half. Right? I'm halving the search space with every guess. Right? So suppose we started with this guess n, Right? We started with the search space of n. After one guess, I will have a search space of n by 2. After one more guess, I will have a search space of n by 4. One more guess, I will have a search space of n by 8. Right? And when will I end? So finally, this search space will reduce down. This search space will reduce down to just one element. Right? This search space will reduce down to just one element. Is that clear? So the question is, how many guesses did it take? So it took me one guess over here. It took me one guess over here, one guess over here, one guess over here, and so on and so forth. So how many guesses? How many guesses did it take? Right? How many guesses did it take? So no, guys, it did not take me n plus n by 2 plus n by 4 all the way till 1. No, this is not how many guesses I got. Right? This is incorrect. So remember that when we are moving from this search space to this search space, I'm making one guess. I'm not making n guesses over here. Right? I made just one guess and I was able to reduce my search space from n to n by 2. Right? So basically, at the 0th guess, when I have not made any guess, my search space is of size n. After first guess, right? After first guess, my search space is of size n by 2 to the power 1. After second guess, my search space is of size n by 2 to the power 2. After the ith guess, my search space will be of the size n by 2 to the power I. Right? Now the question is, at what value of k? At what value of k will this thing become equal to 1? At what value of k will my search space reduce to one single element? And that is the question that we are asking ourselves. So this is the equation that we get, right? So at the kth guess, our search space will be this, and we want the search space to have just one element. So can we find the value of k from here? Can we find the value of k from here? So what can we say? This implies that n equals to 2 to the power k, which implies that I can take log on both sides. Right? I can take log base 2 on both sides, log base 2 of 2 to the power k, right? Which implies that k equals to log base 2 of n. Is that clear? Yes. So I am taking order of log n guesses. I am making order of log n guesses, right? And that is the complexity. That is the time complexity of binary search. Is that clear? Yes. Is that clear, guys? So basically, we started with an array of size n. Then after first guess, we were able to reduce it to half the size. Then after the second guess, we were able to reduce it to 1/4 the size, and so on and so forth. So how many guesses will we take to reduce it to size 1? Well, it will take us log base 2 of n guesses. Right? The depth of this tree, the depth of this is log base 2 of n. Is that clear? Right? Okay. What about the space complexity? What about the space complexity? So let us go to the code to analyze the space complexity. Let us go back to our code and let us see what variables we are using. Okay? So this is our code. Let us see what variables we are using. So we are declaring a variable over here, n. We are declaring a low, we are declaring a high, and we are declaring a mid. Right? All of these take constant space. They are just integers. So overall, our space is just constant. Right? We are not allocating any space that is dependent on the input. We are just allocating a constant space. Right? Notice that this vector, we are not allocating this. This is given to us already. Given to us. Since we are not changing this array at all, so we don't have to allocate the space for the array. All right? The array is given to us. So the space complexity of binary search is going to be simply order of 1. All right? Constant space. Is that clear, guys? Perfect. Now let me ask you a question. Let me ask you a fun question over here. So this is called binary search. Right? This is called binary search. Binary search. Why is it called binary search? Because we are splitting into two parts with every guess, right? And we saw that when we do binary search, our complexity turns out to be log base 2 of n. Right? Our complexity turns out to be log base 2 of n. What if instead of binary search, what if I try to come up with something like ternary search? What if I tried to come up with something like ternary search? So first of all, how would ternary search even work? Right? How would ternary search even work? If I have this particular array, then now I have to guess two values. I have to get mid 1 and I have to get mid 2. Right? This is my low. This is my high. In ternary search, what I can do is I can make two guesses. Right? I can make two guesses. I can say mid 1 equals to low plus high minus low by 3. Right? And I can say mid 2 equals to low plus 2 times high minus low by 3. Yes or no? Can I do that? And then I can compare. Right? Then I can compare. So I can compare AR of mid 1 with my key. Right? I can compare AR of mid 2 with my key. Right? And what will I get? What will I get? Either my key will lie in this area, or my key will lie in this area, or my key will lie in this area. Yes, that is all the possibilities, right? My key cannot lie in both these areas at the same time. Right? My key cannot lie in both these areas at the same time. Does that make sense? So after one guess, we were able to reduce our search space by 1 to 1/3. Right? From n, we could go to n by 3. Right? We could eliminate a larger chunk of our search space. Does that make sense? This is called ternary search. And in general, you can extend this idea. You can define something called a k-ary search. And in k-ary search, what you will do is you will calculate mid 1, mid 2, all the way till mid k minus 1. Right? And then we'll compare with all of them. That will allow us to, in one guess, it will allow us to go from n all the way till n by k. Right? Does that make sense? Yes, ternary means 3 divisions. Binary means 2 divisions. K-ary means k divisions. All right? Is that clear? Example of ternary search? Well, the example is very simple, right? We given an array. What I'm going to do is I'm going to make 2 guesses. Right? Instead of making one guess at any point, I'm going to make 2 guesses. And based on these 2 guesses, I'm going to decide whether I should be looking over here, or I should be looking over here, or I should be looking over here. Right? Going back to our original question, when we were supposed to guess between 0 and 1000. Right? Instead of you giving me a guess like 500, you could have given me 2 guesses at the same time. You could have given me 333 and 666. Right? And then I could have told you that, okay, it is less than 333, or it is between this, or it is above this. Does that make sense? Yes? Does that make sense? Right? So the time complexity of ternary search, it seems that the time complexity of ternary search will be order of log base 3 of n. Right? Because we are dividing by 3 every time. Similarly, the time complexity of k-ary search would be order of log base k of n. Yes? Now, which is greater? Which do you think is greater? Is log base 2 of n more, or is log base 3 of n more, or is log base k of n more? Right? For some large value of k, which value is more? Which value is smaller? Right? So which value is larger? Which value is smaller? Well, if we divide by 2, then it takes us certain number of steps to reach 1. If we divide by 3, then it will take us lesser steps to reach 1. Right? If we divide by 3, then it will take us lesser steps to reach 1. So log base 2 is greater than log base 3n, which is greater than log base kn. Right? So it seems like k-ary search should be the fastest. Right? So why do people still use binary search? Why don't we always have k-ary search? K-ary search seems to be very fast. right? And it seems that I can make it as fast as I want, right? I can just increase the value of k to make it as fast as I want. Yes or no? Yes? Well, let us see what is the fastest value I can have. So maybe when k equals to n, I will get log base n of n, right? Which is simply 1. So I will be able to find the answer in just one guess. That is amazing, right? I will be able to find the answer in just one guess. That's very, very weird, right? I was able to find the answer. I was able to search the element in the array in just one guess if k equals to n. Is that correct? Is that correct? Yes, but there's a catch over here. Right? Now what really happened was we had this array and we made every element as a guess. Right? We made every single element as a guess. And then we checked if our guess is between over here or 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 over here, right? In one guess itself, we made we chose n different values and different midpoints, right? N minus one different midpoints. So are we really doing an efficient search over here? No, this has reduced to the linear search. Right? This has reduced to linear search. So it turns out that when k equals to n, we were expecting it to take just one guess. It did take just one guess, but inside that single guess, we were doing a linear search. Right? So this is the worst thing that we can do. Does that make sense? K equals to n is the worst thing that we can do. So what really gives? We see that our intuition does not equal our math over here. Right? Math says that this should be faster, but intuition says that this should be slower. So what really gives over here? Right? What really gives over here? Well, there's a catch. Right? There's a catch in the fact that this is big O complexity. Right? There's a hidden constant factor. Let us look at the exact complexity of searching. Right? Let us look at the exact complexity of k-ary search. If I'm doing binary search, then I have one guess, right? I have one midpoint. Yes? I have one midpoint. Do you agree? And what check am I making? I'm comparing A of mid with k. Right? How many comparisons is this? This is one comparison. Right? So my actual complexity is 1 times log base 2 of n. Right? This is in the case of binary search. On the other hand, when I have ternary search, I will guess 2 midpoints. Right? I will be guessing 2 midpoints. And then what comparisons do I have to make? I have to compare A of mid 1 with k. I have to compare A of mid 2 with k. Do you agree? Yes, I have to compare A of mid 1 with k, and I have to compare A of mid 2 with k. So how many comparisons is that? This is in fact 2 comparisons. Right? Now you see the hidden cost. As we increase the value of k, the number of comparisons for each guess increase. Does that make sense? Yes, guys. So for ternary search, our complexity is 2 times log base 3 of n. Right? This is for ternary search. And in general, for k-ary search, our complexity will be log base k of n. But for every guess, we will have to make k minus 1 comparisons. Right? We'll have to make k minus 1 comparisons. Now let us ask this question again. What do you think is larger? Right? What do you think is larger? Is log base 2 of n times 1 larger? Or is 2 times log base 3 of n larger? Or is k minus 1 times log base k of n larger? Right? Which one of these is larger? Well, now we know that actually this is the reverse, the other way around. This is the slowest. This is the largest value, so this is the slowest. And in fact, binary search is the fastest. Is that clear? So we can totally do k-ary search. We can totally do a ternary search. We can totally do a k-ary search. but practically binary search will work much faster. Is that clear, guys? Is that clear? Binary search will work much faster. Right? Cool. Now, there's this question. Now you might be thinking that, okay, you told us about ternary search, you told us about k-ary search, and then you said that, okay, those don't really matter, right? Why did you even tell us in the first place? Right? Why did you tell this to us in the first place? The reason is that in certain situations, k-ary search can become faster. Right? K-ary search can become faster. Let us look at how. Right? Let us look at how. Suppose that we are dealing with some sort of a disk, right? Hard disk. Right? Suppose that we are dealing with some sort of a hard disk. Do you know that hard disk is split into blocks and sectors and tracks? Yes. So basically, we are talking about a spinning hard disk over here. Right? We're not talking about that the new SSDs over here. We're talking about that spinning hard disk over here, the magnetic hard disk. So what really happens is, in a magnetic hard disk, you have several platters. Right? You have several platters, and for each platter, you have a read head. Right? You have a read head that is at a particular platter that is tracking a particular track. Right? That is tracking a particular track on this platter. Right? Now, what you have to do is this one track information across this one track is let's say called a track, right? And let us say this is one block. So usually this can be something like 32 kilobytes. This could be 32 kilobytes. All right. Now, what happens is if you have to read any value within this, then that is very fast, right? Then that is very fast because your disk is spinning. Right? Your magnetic disk is spinning at 1000 RPM. Right? So within 0.001 second, you can read this entire 32 kilobyte. You can read this entire 32 kilobyte block. Right? But if you have to change blocks, if you have to move from this sector, if you have to move from this track to perhaps this outer track, right? If you have to do that, then what you have to do is you have to move this head. You have to move this read head. So you have to unplug this read head. You have to run the motor to move it back. Then you have to plug it back, right? And that takes some time. So that moving the read head can take a lot of time. It can take, say, let us say 0.1 seconds of time. Right? So that is very slow. Is that clear? So it turns out that what really happens is it could be the case that due to this thing, it could be the case that making comparisons is fast. All right, you read 32 kilobytes of data in the memory, and then once the data is in your RAM, you are making comparisons in the RAM, right? And RAM is very fast, very fast. On the other hand, making a guess is slow. Making a guess is slow, right? Why? Because for every guess, for making a new guess, you have to change the block. You have to change the hard disk block, right? And you have to move that read head manually, right? Because this is happening at the hard disk level. This is not happening at the RAM level. Okay. So what really happens in this case is making a guess. I want to reduce the guesses. I want to reduce the number of guesses I make. I don't really care about the number of comparisons I make because the comparisons are happening in the RAM very fast, right? So in this sort of scenario, I would prefer to use some sort of a k-ary search, right? I would prefer to use some sort of a k-ary search because in a k-ary search, this is the number of comparisons, right? And this is the number of guesses. This is the number of guesses. The larger the value of k is, the lesser my guesses will be. Right? The larger the value of k is, the lesser my guesses will be. So basically, to maximize my efficiency, I choose a k which is equal to the block size. I choose a k which is equal to the block size. Right? And this thing, right? This thing is used all the time in databases. Whenever you are using a database, the database internally is storing the data in a thing called a B+ tree. Right? In something called a B+ tree. And a B+ tree is simply a binary tree that has been extended from So binary tree works in a binary search manner. Right? On a binary tree, you can have a binary search tree and you can binary search on it. On a B plus tree, you can do a k-ary search. You can do a k-ary search on a B plus tree. All right. How did you come up with this formula? So this formula is what we just saw, right? This formula is what we saw. For binary search, we have one comparison and log-base 2n guesses. For ternary search, we have two comparisons and log-base 3n guesses. For k-ary search, we have k minus 1 comparisons and log-base kn guesses. All right. Is that clear? This is multiplication. Is that clear, guys? All right. So I think we are going to leave it at this, right? We are already above the time. So today we basically discussed binary search. Binary search. We saw how to implement it, right? We saw how to implement it, and we saw that this idea can be extended into a k-ary search, into a ternary search or a generic k-ary search. K-ary search is generally slower, right? Generally, we would like to do binary search, but there are cases, like for example, databases in which k-ary search is very, very valuable. Okay, cool. Now, I would want each of you to, once this lecture is over, to find the link in the video description, or there's a link to the assignment, right? Today's assignment. So please go over there and try to solve those problems. So those problems will be on basic binary search. There are some things that we were not able to discuss, like binary search on a rotated array, right? Finding the peak element. We can discuss it in the next class. All right. All right, guys. Cool. Will we cover interview bit problems from your website? Yes, Reshma. So all these problems. So that is why we give you the assignments, right? We are discussing the problems that are part of those assignments. Okay. I mean, of course, when we are actually doing a scalar class, when someone joins our academy, we usually have 3-hour classes, right? And I mean, we have classes every single day for 3 hours. So that gives us a lot of time to work with the student, right? So they are able to solve many more problems. We won't be able to do that on YouTube, right? So I understand that you won't be able to get the exact same experience as scalar, but that's to be expected, right? Because this is on YouTube. All right then. So please make sure that you solve the assignment. Please make sure that you are taking notes while you're studying the lecture. And see you in next class. In the next class, I will continue. We will continue with binary search, and we will be looking at more advanced problems on binary search. Okay. Perfect. If you want to join Scalar, well, we don't really announce the dates during lectures. So whenever, if you're trying to join Scalar, just go to scalar.com. Right? And any announcement about a new batch, will be made over there. Right? So please monitor the scalar.com website, and any announcement about any new upcoming batches will be made over there. Right? So let us end the lecture then. All right. Bye-bye, guys. Have a nice day. We are back with another lecture. Today we are going to continue binary search. We are going to look at some questions that have been asked in companies, in some of the top companies, right, regarding binary search. Now, without further ado, let us start the class. So let me just share my screen. All right. I hope that everyone can see the screen and whatever I'm writing over here. Cool. So let us start with a question directly. So yesterday we had looked at what binary search was and how to implement binary search. Let us dive into one question today. Okay. So suppose that you have been given an array, right? And this array has n integers. All right. Now it has also been told to you that in this array, all elements but one come twice. All right. Also, it has been said that the array is sorted. So let us first take an example of such an array. Let's look at such an example. Let's say that we have 0, 0, we have 4, 4, minus 4, we have, let's say, 5. All right, we have 5 over here, suppose. Right? Then we have, let's say, something like 7, 7, and we have 8, 8. Right? So in this array, we see that every element has been repeated twice. There are 2 zeros, there are 2 4s, there are 2 7, there are 2 8s, except for one element. Right? Except for one element, every element is repeated twice. Also, this array is sorted. Right? So it is sorted in ascending order. I hope my voice is clear. All right. Cool. Now the question says you have to find this singlet element. Right? You have to find this element which occurs only one time. So if this was the array that was given to you as input, then you are supposed to return 5. Is the question clear? Yes. So we have been given an array. It is sorted. Every element in the array occurs twice, except for one element. And we have to find that one element that occurs only once. All right. So let us see some approaches. So Piyush has a very nice idea over here. Piyush says, let's try XOR. Right now, we all know the property of XOR. We have seen that in the bit manipulation class. That XOR acts like a lock and key. Right? Basically, if I XOR the entire array, that is supposed to give me that element that occurs only once. Right? That element. I'm supposed to get the correct answer because all these things will cancel. Right? 0 XOR 0 will cancel. 4 XOR 4 will cancel. 7 XOR 7 will cancel. 8 XOR 8 will cancel. And I will be left with 5. So yes, that's a valid approach. That is totally a valid approach. What is the time complexity of this? How much time will this take? This will take order of n time, right? Because we have to go over each element and check, right? We have to XOR each element, all right? Cool enough. Can we do better? In this, using this XOR thing, are we first of all making use of this property? We know that the array is sorted, right? So either if we use XOR or if we use a map to keep a count, then we are not really using this sorted property, right? They are going over each element. So let us try to make use of this sorted property and see if we can reduce the time complexity. So this is a valid brute force approach. But let us come up with an optimized solution that exploits the property that the array is sorted. Yes, let us see if we have some other approaches. All right. So yes, binary search would be the answer here. But what exactly are you going to do with the binary search? How exactly are you going to search it? All right. So Anurag over here says that let us check the middle element. All right. Let us suppose we have some middle element. And what Anurag is saying is let us compare it with the previous or next element. Right. And then return. Well, let us suppose that this array was a little longer. Right. Let us say that we had 10 over here as well. So when you find the middle element, let me just add the indices. This is 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Right. So what will be the middle element? This will be the middle element. Right. Cool. Now, if this is the middle element, then we compare it with the left and right element, and what exactly do we do? So we look at both neighbors. All right. This is 5 and this is 7. So how does that help us? It doesn't really help us, right? Okay. So what can we do then? Yes. So Dipanshu has a nice idea over here. Let me just show Dipanshu's comment. So Dipanshu says that let us observe one thing. That whenever a new element comes, it always comes at an even position. Right? Whenever a new element comes, it always comes at an even position. Yes? Is that correct? Until and unless that middle element comes. After that, every new element comes at an odd position. Do you all agree? Yes, the first occurrence of any element is on an even position on the left side of this mid and is on an odd position on the right side of this mid. Do you guys observe that? So we are going to use this property. We are going to use this observation to find out what the single occurrence element is. Right? So suppose that we do something like this. We pick. So we have a high and we have a low. Right? So this is 5 and this is 8. We have a low and we have a high. Right? Let us calculate some mid. Right? Let us calculate some mid. What we will do is this mid will be, let us say, A of mid. Right? This A of mid, it might be the first occurrence of this value or it might be the second occurrence of this value. Right? We don't really know. This 7 that we landed on, this could be the first occurrence of 7 or this could be the last occurrence of 7. Right? We don't really know. So what we can do is we can find the first occurrence of 7. Suppose that we landed on this bit. Suppose that we had landed on this bit. Then we can compare it with the previous element and always find the first occurrence. First occurrence of A of mid. Can we do that? Yes. Given a mid number, can we find A of mid and then can we find the first occurrence of A of mid? It will either be that element itself or it will be just the previous element. Right? Cool. Now once we have that, we can check if the index of first occurrence of A of mid, right? If this is even? If this is even, then what does that mean? What does that mean? That the singlet element lies to the right of me. Right? Whenever I find the first occurrence at an even position, that means that a singlet element lies to the right of me. So I will move right in this case. Right? On the other hand, if this is not the case, if it is odd, then I will move left. Yes? And I will also have to stop at some point. Right? I will also have to stop at some point. So I can check if A of mid is the first occurrence, and there's only one occurrence, right? So A of mid plus 1 is not equal to A of mid. Then I know that I have found my singlet element because it occurs only once. Does that make sense? Yes. So what will be the very quick pseudocode for this? So we will start with low equals to 0. We will start with high equals to length of, so AR dot length minus 1, right? Then we will loop while low is less than equal to high, right? What will we do? So we will calculate the mid first. So we will say mid equals to low plus high minus low by 2. Yes, we just calculated the mid. Remove the extra string comment, surely. Yes, cool. All right, so we calculate the mid, then we can check. So we will first check. So we know that we have to find the first occurrence of A of mid. Right? How do we find the first occurrence of A of mid? Well, we can check over here. We can check if A of mid minus 1 equals to A of mid. Right? If this is the case, then A of mid is the second occurrence and not the first occurrence. Do you agree? Yes, if A of mid minus 1 is equal to A of mid, then A of mid must be the second occurrence because the previous element is also equal to. In this case, what is the first occurrence? The first occurrence is mid minus 1. Right? In this case, the first occurrence is mid minus 1. Otherwise, the first occurrence is mid itself. Right? All right. So what I can do is over here is I can do mid minus minus. Mid minus minus. And then over here, my mid contains the index of the first occurrence. Now I can check. If mid is even or odd. So if mid is even, mod 2 equals to 0, then I have to move towards my right. Yes, I have to move towards my right. How do I move towards the right? I say low equals to mid plus 1. Right? Otherwise, else I move towards the left. I say low equals to, high equals to mid minus 1. I simply say high equals to mid minus 1, right? Perfect. But that does not really tell me when to stop. Right? That does not really tell me when to stop. So I have to make some other checks as well. Also, there is one more problem over here, that what if this mid turned out to be 0? What if this mid turned out to be 0? Then this a of mid minus 1 will give me an index error. Right? I will be trying to index at a negative value. That is not good. Right? So I have to take care of these things. So first of all, what I can do very quickly over here is I can first confirm this. Right? I can first fix this thing. I can say if mid is greater than 0, right, and a of mid minus 1 is equal to a of mid, right, then do mid minus minus. Then do mid minus minus. So after this point over here at this line, mid will be the first occurrence of a of mid. Right? Mid will be the first occurrence of a of mid. Now if mid is even, we do low plus, we increment the low, else we increment the high. But once again, when do we stop? Once again, when do we stop? So we can check over here. If a of mid plus 1, right? If a of mid plus 1 is actually equal to a of mid, is not equal to a of mid, my bad. So we have the first occurrence of this element, right? We have the first occurrence of this element. And if the next element is not the same, then we have found the correct location, right? Then we have found the correct location. So what I can do over here is, let me just erase this and write it properly. And also we'll have to make sure that we check the boundary condition, right? So we will check if mid is less than n minus 1 and a of mid plus 1 is not equal to a of mid, then what do we have? We can just return. We can just return the mid because this is the correct answer. Is that clear? Yes, is the approach clear? So the approach is very simple. The approach is just saying that once you have these elements, all the elements come in pairs, right? All the elements come in pairs. So 0, 1 will come in one pair, then 2, 3, this will be the second pair, then 4, 5, this will be the second pair, until and unless this singlet element comes. Right? This singlet element comes. After that, we will once again have the numbers in pairs. So 7, 8 will be there, then 9, 10 will be there, then 11, 12 will be there, 11, 12 will be there, right? Now notice that before this singlet element, every new element occurred at an even index. Right? Every new element occurred at an even index. But after this, every new element occurs at an odd index. Right? So that is just what we are exploiting. All right? Cool. So what will be the time complexity of this approach? What will be the time complexity of this approach? So Abhay says, what if a of mid minus 1 equals to a of mid, then what are we doing with this? Right? So basically what I'm saying is, suppose we landed at this element. Right? Suppose we landed at this element was 7. Right? This and its previous element was 7. So if this is mid, then we are checking if a of mid minus 1, right? Mid minus 1, if that is also the same as 7, if that is also the same as the same element, then move mid to the left. Right? Then do mid minus minus. Right? That will make sure that we are always looking at the first occurrence of an element. Right? Cool. So the complexity of this is just order of log n. Right? Why? Because this is a binary search, and at every time we are splitting the array into half. We are reducing the search space by half. Right? Is that clear? Cool. So this was a fairly easy question. Let us move on to a slightly more difficult question. Okay. But before that, let me just give you a brief thing. So when you are finding a number in an array, right? You usually return some index. Right? You usually return some index. Now, what occurrence is this? Which occurrence is this? Which occurrence is this? Basically, what I'm saying is, suppose that I have a sorted array 0, 1, 2, 2, 2, 2, 2, 3, 4, 5, 6. Right? Suppose that I have this sorted array. Right? So this is index 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Now suppose I want to find the value 2. Right? I want to find the value 2 in this array. Right? So when I'm searching for the value 2, the value 2 occurs at more than one indices. Right? It occurs at all these different indices. So what index should my binary search really return? That is the question. right? So yesterday we saw that, okay, we were returning an arbitrary index, right? As long as we found the index, it didn't really matter what occurrence we were looking for, right? So I mean, that is perfectly fine, but usually what you will do is you will try to return either the lower bound, right, which is basically the first occurrence, right, or you will return the upper bound, right, which is the last occurrence. Does that make sense? Yes. What if the array is not present? So lower bound is the first occurrence, right? Or if the element is not present, it is the location at which I can insert the element. I should insert the element to keep the array sorted. Yes. Similarly, the upper bound is the last occurrence, right? Is that clear? Yes or no? All right, cool. So basically the question now is that if you have been given an array like this, and I ask you that given a value 2, you have to return both the first occurrence and the last occurrence of this element, then how will you do that? Right? How will you do that? What if lower bound equals to upper bound? Well, that simply means that the element occurs only once. Right, Reshma? That simply means that the element occurs only once. So suppose that the question is that given this array and this value 2, you have to find both the first occurrence and the last occurrence of this array. So basically, if I give you 2, you have to return 2 and you have to return 6. So if the input is this array into, you have to return 2, 6. Right? So how will we do that? Yes, so this is very simple, right? This is very simple. We just have to make sure that we tweak a little bit on those -1s and +1s. Right? We just have to make sure that we tweak a little bit on those -1s and +1s. Right? So usually what we do is we write the loop like this. So while low is less than equal to high, right? And then what do? We say if array of mid, so we have mid calculation over here, we have something over here. We say if array of mid is less than key, right? If array of mid is less than key, then what do? We do lower bound. We do low equals to mid +1. We do low equals to mid +1, right? Otherwise, else if a of mid is greater than key, then we do high equals to mid -1. Right? Otherwise, if it is exactly equal, in the last class we saw that we can just return the mid. Right? We can just return the mid because we have found the location. But now we can't just return the mid. Right? Now, if we are looking for the first occurrence, suppose, if we are looking for the first occurrence, can we return the mid arbitrarily? No, because what could happen is when we calculated the mid, suppose we landed at this particular location. Right? We found the two, but we cannot return it, but because this is not the first occurrence. Right? This is not the first occurrence. So how do I ensure that this is the first occurrence? I will have to check over here that first of all, else if mid should either be 0, right? If the mid is equal to 0, then it is my first occurrence, or a of mid -1 should not be equal to a of mid. Should not be equal to a of mid, right? Because if the previous element is equal to the same element, then this mid is not the first occurrence. Does that make sense? Yes or no? All right, that is fair enough. But then what does really happen then? If I write this code, there is a condition remaining, right? There is some condition remaining over here. Yes, there's some else condition remaining over here, right? So what do I really do in that else condition? Well, I have to absorb that else condition. It will have to absorb that else condition somehow. So basically what I need to do is I need to make this thing less than or equal to key. Oh, sorry, I have to make this thing greater than or equal to key. Right? Basically, If I have found the element, but it is not the first occurrence, then I will still decrease my height. Right? Suppose I found the element over here, but it is not the first occurrence. The first occurrence occurs over here. Then what should I do? I should move left. I should decrease my height. Is that clear? But once again, the moment I do this, something else happens. Right? Another issue arises. What is that issue? That issue is that if I have this condition in my else if, I will never come into the else. Right? I will never come into the else. So what I will have to do is I will have to move this particular condition on the top. Yes, do you guys agree? Do you guys see the problem? Because if I have less than here and if I have greater than equal to here, then I will never go into that else condition, right? These conditions are exhaustive. Yes? So I will have to move this up. So what will my actual code look like now? What will the correct code look like now? For finding the first occurrence, what I have to do is I have to check first of all. If mid is 0, right? If mid is 0, sorry, if a of mid equals to key, right? If I have found the value and either mid is 0 or a of mid minus 1 is not equal to a of mid, right? Only then, if I found the element and it is the first occurrence, only then can I return the mid. Right? Only then can I return the mid. Otherwise, so let me just put it over here. Right? Otherwise, if a of mid is less than the key, then I have to move up. Right? So I can say low equals to mid plus 1. Right? Otherwise, else, I can simply say high equals to mid minus 1. Right? And this is what my correct code looks like now. This is what my correct while loop looks like now. And this is for the first occurrence. Right? This is for the first occurrence. So this code is incorrect, this code is incorrect. Right? And this is the final correct code for the first occurrence. Can you similarly find the last occurrence? Can you similarly find the last occurrence? Yes or no? Yes, you just have to do it the other way around. Right? You just have to do it the other way around. Basically, you have to make sure that a of mid equals to key and mid is equal to either mid is equal to n minus 1 or a of mid plus 1 is not equal to a of mid. Right? That way we find the last occurrence. And when we are finding the last occurrence, this will be less than equal to, and this will not be, this will be less than equal to, right? This will come in less than equal to over here. So that is very simple. It is very simple to find the first and last occurrence of an element in an array. All right. Now suppose that I have an array which is sorted and has size n, and I tell you that given a value x, you have to count the number of occurrences of x in this array. Then what will we do? If we have to count the number of occurrences in this array, then what will we do? Yes? Jay says instead of two binary searches, can we take a while loop both sides and find first and last occurrence? Yes, totally, Jay. We can totally do that. So let us. We are going to explore that via this question. We are going to explore that via this question. Suppose that we have this array. Suppose that we have this array. This element is x, 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 and all the way till this location, it's x. Right? Then this is something else. This is y, y. This is a. So if I am supposed to find the count of x's, this is a sorted array. If I'm supposed to find the count of x's, then I have two options. Either I can find the first occurrence, then write a while loop, then write a for loop, right? Till the last location of x. Yes or no? I can find the first occurrence and then I can increment the count one by one. I can go one by one and till I reach the last occurrence of s. And I can do a count plus plus. Right? I can do a count plus plus. If I do it this way, then what will be the time complexity? What will be the time complexity of this way? Well, to find the first occurrence, it will take me order of log n time. But after that, to count each of these values, I will have to count one by one again and again. Right? I will have to count one by one again and again. So it will take me order of n time for the counting. In the worst case, right? What if the entire array was full of the same values? Does that make sense? So in this case, this approach will be linear. This approach will be linear. On the other hand, can I do something better? Can I do something better? Let me just clear the banner. Just give me a second. Yes, can we do something better? Right? So what we can do is we can simply find the last occurrence. We can simply run a binary search to find the last occurrence. Right? This is one binary search. Binary search. And we can also use another binary search, one more binary search, right, to find the first occurrence. Right? And then we can simply return last occurrence minus the first occurrence. Yes? Is that correct? Plus 1. Exactly. Right? Last occurrence minus first occurrence plus 1. Alright? And that will basically give us the count of that element. Is that clear? Yes? Alright, perfect. Cool. So I hope this is clear, because this is very important. First of all, because whenever you do binary search, you have to understand that you're either going to be finding the last occurrence or the first occurrence. You're not going to be returning any arbitrary occurrence. Also, because in all of the further questions, whenever you are doing binary search, this is going to be very important for us. It is going to be very important for us. So let us look at another question. Let us look at another question. So suppose that we have been given two sorted arrays. Right? This is a very, very famous question. This question has been asked in all sorts of companies, right? Be it Google, be it Amazon, be it Facebook, be it DirectTime. All the companies have at some point asked these questions, this particular question, and this question is very, very, very frequent, right? And even if you try to search on YouTube, you will find hundreds of videos about this question. Right? So this question is very important. The question is that you have been given two sorted arrays of length n and m respectively, right? So you have been given two sorted arrays. One is of length n, one might be of length m. Right? We don't really know which is larger, which is smaller, and both are sorted. Right? Both are sorted. The question is, we have to find the median of both the arrays combined. Right? We have to find the overall median. Yes? Right. So first of all, let us look at what median is. Right? First of all, let us quickly look at what the median is. So suppose that I give you this particular thing. Suppose that I give you this array 1, 2, 3, 5, 5, 6, 8, 10. Right? Suppose that this is my array. And let me put the indices as well. Right? So 0, 1, 2, 3, 4, 5, 6, 7, 8. Right? So what is the median defined as? What really is the median? So median basically is another term for the middle element. Right? This is a loose definition. This is not the exact definition, but median, you can think of median as the middle element, right, of a particular collection. Now, what do we mean by middle element? If you're talking about a middle element, we should have some sort of order. We should have some sort of ordering, right? Yes. So that is why we are talking about a sorted array. So we are saying if we sort a particular array and then we look at the middle element, so in this case, do I have a middle element? How many elements do I have? I have 9 elements in total, right? I have 9 elements in total from 0 all the way till 8. So what will be my middle element? This will be my middle element. Yes, this will be my middle element. Okay. So basically, this is what a median is. Now, some of you might ask, all right, well, what if the number of elements is even? What if the number of elements is even? So let us say that I add up 20 over here. Right? Now I have 10 elements. Right? This is no longer 9, this is 10 elements now. Now there's no middle element, right? The middle element does not exist now. There are two middle elements. Both this and this are middle elements. Yes. Then what is the median? Well, in that case, median is the average of both of these. So in this case, this is both 5 and 5. So the median is just 5. On the other hand, let us try to change the values. So let us say this is 9, this is 9, and let us say this was 8. Right? If this was 8, then what will the median be? It will be 5 plus 8 by 2, right? Which is 13 by 2, which is 6.5. Right? Is that clear? Cool. So this is what the median is. Now the question says that you have two arrays. You have two arrays. Let us suppose 0, 0, 1, 3, 5, 8. Right? And you have another array. Let us suppose 4, 5, 6, 7, 8, 9, 20, 30. Right? Let us suppose that we have these two arrays. So let me put the indices very quickly. 0, 1, 2, 3, 4, 5. 0, 1, 2, 3, 4, 5, 6, 7. Right? Now the question is not asking you to find the median of each of these arrays. That is not what is being asked. What is being asked is the median of the overall array, right? Of the overall collection. So basically, if I were to take all these elements, consider all these elements and sort them, right? Consider all these elements and sort them, then what will be the median? So what will be the median in this case? What will be the median in this case? If I write both the arrays in sorted form, I have 0, 0, 1, 3, 4, 5, 5, 6, 7, 8, 8, 9, 20, 30. Right? Yes or no? And this is 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. Right? That's an even number of elements. So the elements, what? The elements 6 and 7. So the median will over here be, the median will be 5.5. Is that clear? Yes or no? Is the question clear? We have been given two arrays and we have to find the overall median of the two arrays. Is the given array sorted? Yes. Both the arrays are individually sorted in ascending order. Right? Both the arrays are individually sorted in ascending order. Right? But I mean, relatively they are not sorted. So it is totally possible that this element is greater than this element. Right? That's totally fine. Okay. There's no relation between the two arrays. It is just that they are individually sorted. Yes. So yes, Shivani has a nice approach over here. Shivani says that let us very quickly merge the two arrays. So where did our comment go? Yes. So Shivani says over here that what we can do is we can merge the two arrays. So when you were doing the merge sort class, you read this merge algorithm, right? Merge algorithm. What did this merge algorithm do? Given two sorted arrays, it created a sorted array. Yes. And how much time did it take? How much time did this merge algorithm take? So if I have total of n plus m elements, if I have n plus m elements, then usually if I just do sorting, right? If I just do sorting in a naive way, then how much time will sorting take me? It will take me n plus m log of n plus m, right? This is how much time sorting will take me. However, if I use the merge algorithm, given that both the arrays are sorted, then I can do it in order of n plus m time. Yes, I can merge the arrays in order of n plus m time. Once I have merged both the arrays, then I can very quickly find the median. Yes, I can very quickly find the median. Right? Find the median. How much time will it take me? If I have merged both these arrays, how much time will it take me to find the median? So suppose that I have merged both the arrays. After that, how much time is it going to take me to find the median? So is it going to take us order of log n time? No, right? So finding a median is just order of 1. You just have to look at a of mid. Right? You just have to look at a of mid. If the number of elements is even, you just have to look at a of mid and a of mid plus 1. Right? So finding the median takes just order of 1 time, provided that I already have a sorted array. Overall, if I do this merge thing, my overall complexity will be order of n plus m to merge the two arrays plus 1 to find the median. Okay? To find the median, which is just order of n plus m. Is that clear? Order of n plus m. Well, that is fine. That is good. That is certainly better than the naive approach. Right? So this was the naive approach. So this is certainly better, but we can still do better. So this is not the best approach that we can use. So can we still optimize? Can we come up with an optimized approach now? What other approaches we have? So Ratnesh has a very nice question over here. Ratnesh says, can't we just use the median of medians? Median of medians, right? What does Ratnesh mean over here? Let us suppose that we consider these two arrays, right? Let us consider these two arrays separately. What is the median of the first element or of the first array? So this is the first array. What is the median of the first array only? So this array has 6 elements. So the median will be what? So 0, 1, 2, 3, 4, 5, right? It has 6 elements. So the median will be at what index? No. So what Ratnesh is telling us is that let us try to find the median of medians. Right? Let us try to find the median of medians. So first of all, let us consider this particular array, A1. Right? This particular array has how many elements? It has 6 elements from this location to this location. So what will be the median of this particular array? It will be the sum of these two. It will be the average of these two, right? It will be 1 plus 3 by 2, which will just be 2. Right? Similarly, let us calculate the median of this array. Let us calculate the median of this array. Well, how many elements does this array have? This has 8 elements, right? And what is the median of this element or this array? That will be this 3 plus 4, right? This element at 3 and element at 4. So that is 7 plus 8 by 2, which is 7.5, right? Now, Ratnesh is saying, once we have these two medians, can't the final answer simply be the average? Can't the final answer simply be the average of these two? 2 plus 7.5 by 2? Well, no, that is not going to be always true. Right? That is not going to always be true. Is that clear, Ratnesh? Over here, we see that this does not really work. This is 9.5 by 2, which is 4.75. Right? And that is not the answer. The correct answer is 5.5 over here. So it doesn't really work. All right. So let me just remove Ratnesh's comment. So median of medians will not work over here. So we have to do something else. Yes. So what approach can we use? What approach can we use? So now we have to do some sort of a binary search. Right? We can use some sort of a binary search to optimize the solution. Right? So what we are going to basically do is we are going to binary search. There are multiple ways of doing this. Right? We are going to binary search on the index only of. We are going to binary search over the smaller array. Right? So first of all, suppose that this is A1, suppose that this is A2, right? So can I assume without loss of generality that A1 is smaller than A2? Can I assume that the length of A1 is smaller than length of A2? Yes. If that is not the case, then I can just swap those arrays, right? I can call this A1 and this A2 if that is not the case, right? So let us assume that A1 is the smaller array. So what we are going to do is we are going to binary search in this smaller array. All right. So we will have some low, we will have some high, and we will calculate a mid. All right. Now, once we have this mid, the question is, when will A1 of mid be the correct median, be the answer? What has to be true? What has to be true for A1 of mid to be the correct median? What has to be true? If A of mid is the correct median, then how many elements in A1, are less than mid A of mid? How many elements in A1 are less than A1 of mid? When all these elements are less than A1 of mid? Yes or no? Do you agree? And how many elements are greater than this? Well, all these elements are greater than it. Yes. If A1 of mid is actually the median, right? Then what must be true? What must be true? Then half of the elements, right, across both the arrays, half of the elements must be less than it and half of the elements must be greater than it. Yes, half of the elements must be less than it, and half of the elements must be greater than it. Cool. So let us check. Let us quickly check. So if A1 of mid is actually the median, then how many elements in A2 should be? Or if this is the case, if is actually the median, then how many elements in A2 should be less than A1 of mid? Right? That is the question. Right? So we know that in A1 there are mid minus 1 elements. Oh, there are mid elements, mid number of elements. So the count of elements in A1 that are less than mid is mid. Right? So the total number of elements that have to be less than A of mid. The total number of elements that has to be less than A of mid should be n plus m by 2. Yes or no? Should be n plus m or plus 1 by 2 actually. Do you guys agree? If I have this total sorted array, and this is actually the median, then half the elements will be less than it and half the elements must be greater than it. So if this many elements are less than it overall, right? And out of these, this many elements were already present in A1. This many elements were already present in A1. Then what is the number of elements that are present in A2 which are smaller than this A of mid? So this many elements were already present in A1. So this must be the number of elements. This must be the number of elements in A2. Number of elements in A2 that are less than mid. A of mid. Yes? Does that make sense? How can you say that length of A1 is equal to mid? No. We are not saying that the length of A1 equals to mid. We are not saying that. We are saying that assume that mid is the correct median. Assume that mid is the correct median. For that to be true, if there are these many elements that are less than it in A1, then how many elements should be less than it in A2? And this is the answer. This is the answer. These many elements should be less than mid in A2. So what we can actually do is, we can start with some low over here. We can start with some high over here, and we can calculate a mid. Now what we can do is, we can put a marker at n plus m plus 1 by 2 minus mid. Right? We can look at this particular index. Right? We will have 4 elements now. We will have 4 elements. We will have one over here, one element over here, one element over here. Right? So let us call these elements A, B, C, D. Let us call these elements A, B, C, D. A, B, C, D. Right? Now, when is this A of mid? When am I at the correct position? I am at the correct position when A is less than D and B and C is less than B. Right? If this is the case, then this marker, these two markers, they point to my median. Do they not? Yes. Do they not point to the median? Why do they point to the median? Because the number of elements over here and the number of elements over here is equal. Do you guys agree? The number of blue elements is equal to the number of green elements. Yes, and how are they equal? Because I have chosen to be. Right? Because I have used this formula to make sure that I land at the correct spot over here. Does that make sense? Cool. So, guys, if this is not clear to you at the moment, we will make sure to basically explain this with an example. Okay. So we will look at a concrete example. But let me first explain the idea. Right? So basically, what we have to do is we have to binary search for a mid such that the property of the median, becomes valid. Right? Now look at a concrete example. Let us look at a concrete example to further establish this. Right? Suppose that we have this array 0, 1, 1, 3, 5, 7. All right, and we have another array. Suppose 4, 5, 6, 8, 8, 12, 20, 30. All right, and let us mark the indices 0, 1, 2, 3, 4, 5, 0, 1, 2, 3, 4, 5, 6, 7. All right. Now, which one is A1 and which one is A2? Which one is the smaller array? This is the smaller array and this is the larger array. Yes, this is the smaller array and this is the larger array. So let us have 2 pointers. Let us have the low pointer and let us have the high pointer. Yes, let us have the low pointer. Let us have the high pointer. Also, what is the value of n? The value of n over here is 6. And what is the value of m? The value of m is 8. Yes, there are 6 elements in the A1 array and there are 8 elements in the A2 array. Yes or no? Cool. So now we have this low and high. What will be the mid? What will be the mid? Mid will be 5 by 2, which will be 2. Yes, mid will be 5 by 2, which will be 2. So this is the midpoint. This is the midpoint. Alright. And A1 of mid equals to what? It is 1. Right? Now the question is, how many elements in A1 are less than or equal to A1 of mid? How many elements in A1 are less than or equal to A1 of mid? Well, these many elements, right? This element and this element. Yes, there are 2 elements that are less than or equal to A1 of mid. What is the count of that? Well, the count is simply mid. Right? Mid is the count. Do you agree? Right. Now, if this one was actually the median, then how many elements should in this array should be less than 1? Right? In this array, how many elements should be less than 1? Well, total there are 14 elements. Right? Total there are 14 elements. So if there is my median, then half of the elements must be less than it, half of the elements must be greater than it. Right? So basically what I'm saying is 7 elements should be less than or equal to it, 7 elements should be greater than or equal to it. Right? That is the property of my median. Right? Yes or no? Cool. So basically, if this is the case, and two of these 7 elements come from A1, right? 2 of the lesser elements come from A1, then how many lesser elements should come from A2? How many of the lesser elements should come from A2? Well, 2 are from A1, so 5 must be from A2. Right? 5 must be from A2. So all these elements should be less than 1. It should be less than this 1. If 1 was the median, then all these elements should be less than 1. Are they less than 1? Are they really less than 1? Yes or no? They are not less than 1, right? So 1 cannot be the median. Does that make sense? Because all these elements, they are not less than 1. So 1 cannot be the median. So my median is too small. In that case, I have to increase my load. Right? I will try to find the median on the right hand side. Is that clear? Is that clear, guys? Yes. So basically what we are saying is that let us say that we are going to have a low and we are going to have a high, and we are going to calculate the mid as low plus high by 2. Right? Now, how many elements are less than mid, A of mid in the first array? Well, that is just mid. So how many elements should be less than it in the second array? How many elements should be less than it in the second array? That should be what? That should be n plus m plus 1 by 2 minus mid. Yes, that should be n plus m plus 1 by 2 minus mid. Right? So what we can now do is, so this is the partition. This is basically the partition of A2. Right? Now we can simply check. Now we have 4 elements. We have A1 of mid. We have A1 of mid plus 1. Right? And we have A2 of partition. And we have A2 of partition plus 1. Right? Is that clear? And we can check if this element is less than this element and this element is less than this element, then our partition is valid and we have the correct midpoint. Right? Then our partition is valid and we have the correct midpoint. All right. Why n plus m? Why this plus 1 thing? Well, this is just to make sure that the number of elements that are on the left are greater than or equal to the number of elements on the right. Right? That is just to make sure that the number of elements on the left are either equal to the number of elements on the right, or they are one more than the number of elements on the right. Okay. So if the number of elements is even, then there will be a mismatch, right? You can't have both the same number of elements on both left and right. So we will have one extra element on the left. Is that clear, guys? Just give me a second. Let us look at some code for this. Right? Let us look at some code for this. So what will really happen is, let us suppose that we have 2 arrays. So we have find median, and we have two arrays. We have A1 and we have A2. Right? Let us call this A and B. Let us call this the array A and the array B. All right, for simplicity. Now what we are going to do is we are going to make sure that array A is smaller. We are going to make sure that array A is smaller. How can we make sure that array A is smaller? How can we make sure that array A is smaller? Well, we can declare it over here, right? So we can say if the length of A dot length is greater than B dot length, right? If it is in fact larger, then simply swap the values of A and B. Right? So this will ensure that that this particular array is smaller. Right? And notice that this swap is just swapping the pointers. This is just swapping the pointers. This is not actually moving the arrays. This is just swapping the pointers. All right. So now that we have ensured that A is the smaller element, so now what we can do is we can have a low and we can have a high. Right. So we can say that, all right, low, we can initialize low equals to 0 and we can initialize high equals to what? So what array are we searching over? We are searching over the smaller array. We are searching over the smaller array. So we will say high equals to A dot length. Right? A dot length, right? And basically, let me also do one thing. Let me also save two values over here, n and m. So let me say, for simplicity, let me say that n equals to A dot length and m equals to B dot length. B dot length. Right? So we have saved the length or the length in nm. So now my low will be 0 and my high will simply be n. All right. Now I can loop. While my low is less than or equal to the high. Right. Now what is the first thing that I should do? The first thing that I should do is I should calculate the mid. Right? I should calculate the mid. And what is the mid? The mid is simply low plus high minus low by 2. Right? Cool. Now this mid is a marker in the first array. This mid is a marker in the first array. What will be my corresponding marker in the second array? As we just saw, that corresponding marker, that is called this partition, right? This is called this partition. This is going to be n plus m plus 1 by 2 minus mid. Right? Is this clear to everyone? Is this clear to everyone? That this will be the partition? Cool. Now what we are going to do is, we are simply going to compare values. We are simply going to compare values. We are going to say that if, okay, we are going to say if A of mid, right? If A of mid is less than or equal to B of partition plus 1. Right? If A of mid is less than or equal to B of partition plus 1 and A of mid plus 1, or basically I can write it the other way. I can write B of partition is less than A of mid plus 1. Right? If this is the case, then what do we have? What do we have? We have two arrays. We have two arrays such that this element is smaller than this element, right? And this element is smaller than this element, right? So A is less than B and C is less than D, right? And we know that the number of elements over here is equal to the number of elements over here, right? If this is the case, then I have found my median. Right? So I have found my median over here. So I have found the correct midpoint, right? And I will actually return the median over here. So we will have two cases over there as well. We will look at that. But if that is not the case, then some other case will arise. Right? Then some other case will arise. What case can arise? What case can arise? So either it can be that A is actually greater than B. Right? It can be that A is greater than B, or it could be that C is greater than D. Yes or no? If A is in fact greater than B, let us suppose that I have something like 5 over here and 7 over here, right? And I have something like or let's say 12 over here and sorry, not 12. Let us say 1 over here and 3 over here, right? So if this element is greater than this 3, then what does that mean? If this element happens to be greater than this 3, then what does that mean? It means that my midpoint is too high. This midpoint is too high. right? I have to move left. Is that clear? Similarly, if that's the opposite thing, right? If I have 5 and 7 over here, right? If I have, let's say, 12 and 15 over here, right? So if this element is greater than this element, right, then my mid should be on the right. Right? This value 7 over here, this is too low. So I should move to the right. Right? So that is what we are going to do over here. We are going to say else if A of mid is greater than B of partition plus 1, then I have to increase my mid. Right? So I have to decrease my mid. Right? So I will say high equals to mid minus 1. Right? Otherwise, I will say low equals to mid plus 1. All right. So this is the main while loop. Now there are some more conditions that arise. Those conditions are basically, let us take one more example. Let us suppose that we have this particular array and we have this particular array. Right? All right. Now we have two conditions. Either the combined length n plus m, either this is even, or n plus m, this is odd. Right? Either this is even or this is odd. If the length is odd, then what will be my median? If the length is odd, then what will be my median? This is A, B, C, D, right? We know the number of elements over here. So the number of blue elements is either equal to number of green elements, or it is equal to green elements plus 1. Right? It is either equal to it or one more time. Right? So if I found the correct midpoint over here, then what can I say about the median? The median has to be one of these two things. Right? The median has to be one of these two things. Yes or no? Yes or no, guys? And which one of these is the median going to be? Is it going to be A or C? Well, it is going to be the maximum of A comma C. Yes, the median over here is going to be the maximum of A comma C. On the other hand, if the number of elements are even, then what do I have? Well, in that case, what do I have? I have the max of, I want to find the maximum value on the left, right? I want to find the maximum value on the left. So max of A comma C, and I want to find the minimum value on the right. Right? So a min of B comma D, and I want to take the average of those, because the median will be average of two different values over here. Right? I want to take the average of those. Is that clear? Cool. So basically, what do I have to write over here? I have to check if n plus m mod 2, right? If n plus m mod 2 equals to 0, if it is even, then I have to return basically A of max. So basically I have to return max of A of mid comma B of partition, right? The max of these two plus the minimum of A of mid plus 1 comma B of partition minus 1, right? And I have to take the average of these two. So I will add these two up and I will divide by 2. Right? That's a very long line, but I hope that it makes sense. Right? That is the case when my number of elements is even. On the other hand, if the number of elements is odd, then this is very simple. Right? I simply return. So I can simply return over here the max of A of mid and B of partition. All right, we can simply return the max of A of mid or B of partition. So this will basically be the code for finding the median of two arrays. Now there's one bug over here. Can someone catch that bug? This code is not entirely correct. There is one very, very crucial bug over here. And that bug is basically, let us suppose that I was searching in this array and I was searching in this array. Right? Suppose that while searching this array, either my midpoint became n minus 1, or if my midpoint became 0. Right? Then what do I compare? I don't have anything to compare, right? If my midpoint is this thing, n minus 1, then I can't compare a of mid plus 1 with anything, right? I can't really compare a of mid plus 1 with anything. Yes or no? So for that, to handle that, we can very simply, we can virtually append infinity and minus infinity to the left and right of both the arrays. All right? Yes, exactly. So Jay, even in that case, if the first array is only of size 1, so we will very quickly exhaust the mid. Right? We will very quickly exhaust the mid. So to handle that situation, to handle that boundary case, we need to add infinity and minus infinity on the right and left side of both the arrays. All right? You don't have to actually append it. You can treat it virtually. Right? You can treat it virtually. Is that clear? Yes, आज कुछ ज़्यादा हो गया. Well, I mean, I would recommend that you actually try and code this up. When you try and code this up, this will, so I understand that you won't be able to, you will have to get practice on this. You will have to actually try and code this up to properly understand this. Right? But I hope that the intuition was clear. The code might not be clear to you, but I hope that the intuition was clear. Right? Cool. So now what will be the time complexity of this overall algorithm? What will be the time complexity of this overall algorithm? Yes. So we are doing a binary search, right? We are doing a binary search over what? We are doing a binary search over the smaller array. Right? We are doing a binary search over the smaller array. So what will be the time complexity? It will be order of min. So it will be order of log of min of n comma n. All right. It will be order of log of min of n comma n. Is that clear? Yes, Himadari, there are a lot of edge cases over here. So we always have to take care of the edge cases. I mean, the solution is very elegant, but the code only becomes difficult because of all the edge cases that you have to handle. All right. Tushar says, how are the corner cases rectified? The corner cases can be rectified by just adding a minus infinity to the left of both the arrays and a plus infinity to the right of both the arrays. All right. Basically, you can say that you have 4 values over here, right? You have 4 values over here. You have A, B, and you have C, D. You have these 4 values over here. Well, what if this midpoint was equal to n minus 1? In that case, if that is the case, then there is no A of mid plus 1, right? There is no A of mid plus 1. So what value should you consider instead of B? There is no B. B does not exist, right? So what value should you consider instead of B? You should consider infinity. Similarly, this value over here, if this is partition and this is partition plus 1, right? If there is no D element over here, then you should consider infinity in its place. Similarly, on the left hand side, if mid is 0, then on the left hand side you should consider minus infinity, and same for partition. Is that clear? So once you actually try to code this, things will start making sense. I don't want to give you the exact code right now, because then it will defeat the purpose of us trying to solve these questions. All right, you actually have to code this yourself, struggle a little with the edge cases, and once you figure this out, things will become clear. All right, cool. So let us move on then to the next question. Right. So the question goes something like this. That we have an unsorted array. Right, of size n. All right, and this array only has positive integers. Right? We have an unsorted array of size n, and this array only has positive integers. Now we have been given a value. X, right? And we have to find the largest value of k. The largest value of k, such that no subarray of length k has sum greater than or equal to x. or let us say just sum greater than x. All right. So that's a mouthful. That's a mouthful. Basically, what we are saying is, suppose that we have some array with some elements. Right? We have some array with some elements, and we have been given a number x equals to 10. Right? Let me also give this array. So this is 1, 5, 6, 2, 0, 1, 3, 5. All right. Let us say this is my array, and I have been given some x equals to, let us make this a little smaller, perhaps x equals to 6. Right. Now we have to find the largest window size. Right? K is the window size. We have to find the largest window size such that in that window there is no window that sums up to greater than 6. Right? There is no window that sums up to greater than 6. So in this case, what will be the answer? In this case, what will be the answer? Is the question clear? So if I make a window of size 1, if I make a window of size 1, this or this or this or this or this or this, then is the sum ever going to be greater than 6? Is the sum ever going to be greater than 6 if I have a window of size 1? No, right? So window of size 1 is valid. Right? Window of size 1 is valid. Size 1 is valid. Right? On the other hand, if I have windows of size 2, let us say this window, right? What is the sum of this window? The sum of this window is 6. Right? So 6 is okay. What is the sum of the next window? 5 plus 6. The sum of this is 11. Well, 11 is greater than 6. Right? 11 is greater than 6. So this window is not okay. And because this window is not okay, the window of size 2 is not valid. Right? Windows of size 2 are not valid. Is that clear? Okay. So we know that a window of size 2 will give me a sum greater than 6. So should I try a window of size 3 or above? Should I try a window of size 3, size 4, size 5? Yes or no? I should not try them, right? There is no point in trying them. Does everyone agree? Yes, because we have to find the largest window such that the sum of any sub-array of that size must be less than or equal to this summation value over here. Right? Let us take another example, perhaps. Let us take another example. So let us take one more array. So suppose this array is 1, 0, 3, 6, 4, 2, 7, 0. Right? And let us say that x equals to 13. Right? Let us say that x equals to 13. Okay. Now, what is the largest window? What is the largest value of k such that no window of size k has sum greater than 13? Right? So does k equals to 1 work? Does k equals to 1 work? If I have windows of size 1, then is the sum going to be greater than 13? No, right? So windows of size 1, they all have sum less than 13. Right? So windows of size 1 are valid. Right? Every window of size 1 is valid. So size 1 is valid. This is valid. All right. What about windows of size 2? What about windows of size 2? Well, this has a sum of 1. This has a sum of 3. This has a sum of 9. This has a sum of 10. This is 6. This is 9. This is 7. Right? All the sums were less than or equal to 13. So windows of size 2 are also valid. All right. Let us try increasing the window size further. K equals to 3. All right. Now, what do my windows look like now? My windows are, so this is my window, first window. Right? What is the sum of this? It is 4. Then this is the second window with sum 9. This is the third window. Right? This has sum 13. This is the fourth window. This has sum 12. This is the fifth window. What is the sum of this fifth window? This is still 13. This is the last window. This has sum 9. Right? So still we see that window of size 3 is also valid. Is that clear? Window of size 3 is also valid. All right, let us try to increase it further. So let us try k equals to 4. All right, now what is the size of what is the sum of this? That is 10. What is the sum of this? That is 15. Right, the sum of this particular window is 15, and 15 is already greater than 13. 15 is already greater than 13. So windows of size 4 are not valid. Is that clear? And because windows of size 4 are not valid, windows of size 5, windows of size 6 will also not be valid. Right? All these will not be valid. Is that clear? Yes, is that clear? So if this is my array, if this is the input array, and this is the value of x that has been given to you, then what value of k should you return? what value of k should be returned? We should return k equals to 3. Right? We should return k equals to 3 because we have to return the largest size of window, so that no window of that size has sum greater than x. Is the question now clear? Yes, is the question now clear? All right. So how can we approach this particular question? So guys, whenever you come across a new question, don't try to come up with the optimized approach right away. Right? Come up with the most brute force approach. Right? First, try to solve the question. Once you have solved the question, then you can try to optimize it. Right? Because some solution that works but is slow, some solution is always better than a fast solution that you never find. Right? So having some solution at least is better. Right? So let's think of brute force approach first. Yes. So what can we do? All right. So let us look at two questions. Suppose I have a guess. Right? Suppose I have a guess for k. Right? Suppose I say that k equals to, let's say, 5. Right? Suppose I have this array and I have been given a value of x, let's say 20, and I am guessing that k equals to 5. Then how can I verify? How can I check it? I have to consider every possible window of size 5. So how can I do that? I can either do two nested loops. So I can either say for I equals to 0 all the way till n minus 5 minus 1, right? For j equals to 0 till 5 minus 1, right? And then I can say sum plus equals to a of j, a of I plus j, right? And initially sum equals to 0, right? So doing this, what will this do? This will give me, so only, sorry, over here, I will have to say sum equals to 0 over here. So basically, after this inner loop, in each iteration of this inner loop, I will have the sum of one window. Right? I will have the sum of one window again and again. So I will have to check if sum is greater than x, then return that window size is invalid, right? K is invalid. Right? After this entire thing is complete, I can say that k is valid. Right? So given a window size k, this is how I can check it. Yes or no? That seems like a very, very difficult approach to do, right? So can we simplify this a little bit? How can we do that? So are you guys aware of prefix sum? Suppose that this is my array. And I want to find the sum from some start location to some end location. Right? If I want to do many queries of such form that find the sum of all these different elements, then how can I do that efficiently? I can calculate the prefix sum of the array. Right? Let us say that this is the array A, then the prefix sum of array A will be P of A. Yes. Now, if I were to tell you to calculate A of I plus A of I plus 1 or plus A of I plus 2 plus all the way till A of j, then how can you express this in the form of prefix sum? Well, this is simply equal to what? P of j minus P of I minus 1. Yes or no? Is that clear? Yes or no, guys? Alternatively, you can also rewrite this as P of j minus P of I plus A of I. Right? You can also rewrite this as this. They are the same thing. All right. So once I have this prefix sum, if I tell you that find me the size of window of size 5 starting from this location I. Right? If I ask you to find the sum of this window, then how can you do that? How can you do that? You can very simply do what? You can simply do prefix sum of I plus k minus prefix sum of I minus 1. Yes or no? This will give you the sum of this window. Right? And to go over all possible windows, you can just write a loop for I equals to 0 all the way till n. Right? N minus k basically. Yes? So that is the first thing that we can do to make our sliding window calculation a little simpler. Right? We can store the prefix sum. But the thing still comes that, all right, given a value of k, I can check if it is correct or not. But how do I find the value of k? How do I find the value of k? Currently, the approach that I have is start from k equals to 1 and try increasing it. Right? Try increasing it one by one. Right? If I do that, then what will be my time complexity? I will have a loop for k. This will run for order of n time. Right? Then I will have a loop for checking k. This will also run order of n time. So my total time complexity will be order of n squared. Yes. Of course, I also have to consider the complexity of the prefix sum. But calculating the prefix sum is just order of n pre-computation. Right? Pre-computation. So this is actually order of n squared plus n, which is just order of n squared. Right? This is my naive. This is my brute force algorithm. All right. Can we improve this? So Teju says that we can use binary search. Right? But what should we binary search over? Teju, what should we really binary search over? Yes, so Prakash says that we can binary search for the value of k. So we are going to binary search for the value of k itself. Right? So what is the minimum possible value of k? What is the minimum possible value of k? What is that? What is the minimum possible value of k, guys? It is 0. Right? It is 0. Basically, if some a of I itself is greater than x, then I can't have a window even of size 1. Right? In that case, the value of k will be 0. On the other hand, what is the maximum possible value of k? That is n. Right? If I take if the sum of the entire array is still less than x, then that is the maximum possible value of k. So what I have to do is I have to binary search in this search space. So I can say low equals to 0, high equals to n, while low is less than equal to high. Right? I will say mid equals to low plus high by 2. Right? All right. Now, once I have the mid, what should I do? I should check window of size mid. All right? I should check window of size mid, and I will have another function over here. Check window. Right? That takes a value of k and returns true or false. Right? This check window is going to do exactly this. So it is going to loop. It is going to say for I equals to 0 all the way till n minus k. Right? If the prefix sum of I plus k minus prefix sum of I minus 1, right? If this is greater than x, if any of this sums is greater than x, then return false. Right? Otherwise, return true. Right? If all these windows are valid, then return true. Right? This is the check window functionality. Is that clear, guys? Cool. So we have a function for check window now. So what can we see over here? So if I check window of mid and this comes out to be true, if check window of mid comes out to be true, then what can I say? If a window of size k works, then can I return this? If a window of size k works, then can I return that window size as the final answer? Yes or no? No, I cannot. Because yes, this works, but this might not be the largest value that works. I have to find the largest value that works, right? So if this is the case, then I have to increase my low. So I will say low equals to mid plus 1, right? Mid plus 1. On the other hand, if this does not work, then I have to decrease my value of k, right? So else I will say high equals to mid minus 1, right? High equals to mid minus 1. Well, when do we stop? When do we stop? So we can either stop when this loop exits, or we can explicitly check. We can explicitly check that k works, but k plus 1 does not work. Right? If that is the case, then we can simply return. Is that clear? Even if you don't do that, that is fine, because this loop will will automatically take care of it. Is that clear? So we will return when we find a position of k which works, but the immediate higher position, right? K works, but k plus 1 does not work. That will be our correct answer. Is that clear, guys? So after this loop, after this while loop is over, I can simply return what? What can I return? So this will exit when low will become greater than high. Right? Low will become greater than high. How will it become greater than high? When I would just do low equals to mid plus 1. Okay, so I can just return low over here. Right? I can just return low over here, and that will be my size of the window. All right, cool. So what will be the overall time complexity of this algorithm? What will be the overall time complexity of this algorithm? So let us take this step by step. How much time does check window take? How much time does one function call to check window take? This is simply a for loop. Right? This takes order of n time per call. Right? This takes order of n time per call. Well, what about this thing? This is login search. Right? This is login search. But inside this login search, we are doing this order of n call every time. Right? Inside this login search, we are doing this order of n call every time. So basically, the time complexity will be order of n times log of n. Yes, order of n times log of n. Well, we also have to consider the prefix something. So this is for the prefix sum. This is for the binary search. Binary search. Oh, sorry. This is for the binary search. This login thing. This is for the binary search. And this is for check window. Check window. Right? So the overall time complexity is just order of n log n. Is that clear? All right. So let us end the class at this point. Bye-bye. Have a good day. Hello, everyone. So we are back again with another class. All right. So today's topic is once again binary search. So we have been studying binary search in the past 2 lectures. Right. So if you have not watched those past 2 lectures, please go and watch them. So let us continue with some more advanced problems on binary search today. All right. Let me just share my screen. I hope that everyone can see the screen. All right. So let us start with a question that you might have seen earlier. Right. It is a pretty famous question. And you might have seen this in the arrays, 2D arrays class that we already had. Right. But this question is relevant to binary search, so let us quickly see it here once again. Question goes something like this. You have been given a matrix. I mean, this is not that matrix movie thing. This is a matrix. It's a 2D array, right? Now, this matrix can have a certain size. Let us say that the size is n cross m, right? Now, there's one property in this matrix that each row and each column is sorted, right? So let us quickly take an example of what one such matrix would look like. So suppose we have 10 over here, 20, 30, 40, 50, right? All right. What other numbers can we choose? So let us suppose that we have 15, 25 perhaps, 35, 45, 55. Something else, maybe 27, right? 29, 37, let us say 48, and let us say 60, right? So let us just add quickly one more row. So suppose this is 32, and suppose this is 40, suppose this is 51, suppose this is 60, and suppose this is also 60. right? So we see that in this matrix, every row individually is sorted, right? Every row individually is sorted, and so is every column. So is every column, right? Cool. All right. Now, what is the size of this particular matrix? Well, over here we have 4 rows, so n equals to 4, and m equals to, we have 5 columns, so m equals to 5. So this is a 4 cross 5 matrix, right? Now we have been given an integer. We have also been given an integer k. Right? So k stands for key. We have been given a key, and we have to search this key. We have to search this key within the matrix, and we have to return. We have to basically tell whether the key exists or not. Key exists or not. Fair enough? Yes. All right. So Rahul has a question over here. Rahul, I guess, is talking about the assignments that were given in the last class. Rahul says that 5 questions in 24 hours is kind of aggressive. Right? So Rahul, you do not have to attempt those questions in 24 hours. Right? So unlike when you are enrolled in Skiller Academy, you will have a lot of guidance. You will have mentors, you will have TAs that will be helping you while you're working through the assignments. Right? We will have remedial classes a lot. When we are on YouTube, we just want to give you as many assignments as we can so that you can practice on your own time. Right? So it could be the case that yesterday, after taking the class, you were able to solve 2 of the problems. Now, maybe 5 days later or 10 days later, you want to come back and try it again. Right? So we just want to make sure that you have some new problems that you can still attempt. All right? So do not worry about the time constraint. This assignment is not timed. Right? So feel free to take this assignment whenever you want, how many times you want. So it doesn't really matter. Okay. Just the assignment is just to make sure that you can practice a lot. Perfect. So yes, Shazia is saying that this question has been done in the previous class. So we are going to very quickly move through this question. All right. But this is kind of important for binary search as well. So as you guys already know that this is binary search question. So let us just quickly recap this. All right. Perfect. So this is the question. You have been given a matrix of size n cross n. Each row and each column is individually sorted. Given a key, we have to find whether this key exists in this matrix or not. Yes. Perfect. So what approach do we have? Well, one of the brute force approaches. So whenever we have a new problem, we try to come up with a brute force approach. Brute force approach, right? In a brute force approach, we will not be using any extra information that we are given, right? So what will be the brute force approach? We simply try to linearly, so linear search. If we search through the entire matrix in a linear manner, then how much time is it going to take? What will be the time complexity? Well, how many elements are there? There are total n cross m elements. We are doing a linear search, so it will be the complexity, the amount of time it will take us for linear search will be order of n cross m. All right, but we can optimize, right? We know that each row and each column is individually sorted. Interesting. Well, let us just worry about the rows for now. Let us just worry about the rows for now. So we know that because each row is sorted, we can binary search. Inside each row. Is that correct? So if we binary search, let us call this binary search 1. If we binary search inside each row, then how much time is it going to take us for every row? Well, there are m elements. Well, there are m elements in a row, right? There are n rows and there are m columns. So every row has m different elements. So if we want to binary search among m elements, it will take us log of m time. Right? This is for one row. Now we have to do this for all the rows. How many rows are there? N different rows. So it will take us order of n times log m time. Yes, do you guys agree? On the other hand, if we basically, so this is on the rows. If we binary search number 2 on the columns, right? Then it will be very simple. So it will be m times log of n, because now we are searching within each row. Right? We are searching within each column. And how many elements are there in a column? Well, equal to the number of rows. So we can search through a column in login time, and we have m columns to search through. Right? So if we search through just the rows, we will get this complexity. If we search through just the columns, we will get this complexity. The question is, can we do better? Right? Now, this might not be obvious from the question itself. We have already tried binary searches. Right? We have already tried binary searches, but binary search is not always about this binary property. So just because you are saying binary, that does not mean you always have to split the array into half. Right? That is originally what binary search means. But binary search has a more important concept, more important underlying concept. And the concept, as we discussed in the previous classes, is what? The concept is that given a search space, when you make a guess, you are able to eliminate a large part of that search space, right? So every guess allows you to eliminate a large chunk of the search space. Perfect. All right. So that's fair enough. So how can we basically do that? For this particular question? Well, we can observe. Let us suppose that we are looking at this particular element. Right? Let us just pick any random element, and let us say that we are looking at this particular element. Right? Then, if we determine that given our key, right? Let's say that we compare this key with 45. Suppose that the key is less than 45. Right? Suppose that we are looking for an element like 29. 29 is less than 45. Right? Then what can we know from here? This key was less than 45. So can this key be over here? Can this key be in this area? No, right? This key cannot be in this area. Why? Why can it not be in this area? In fact, this particular area, because this key is less than 45, and everything in this area, everything over here in this area is already greater than 45, right? So the key cannot be over here. Similarly, so I can reduce my search space, right? I can reduce my search space by a large chunk. This might be a large chunk. Now there's one more property that we get. If we move in a particular order, right? Suppose that we are starting from the top right, then we can also eliminate some more rows or some more columns. Right? So we will see that we will be able to eliminate this top row as well. Right? So over here, there's nothing binary over here. Right? We are not really splitting the search space into half. However, what we are able to do is we are still able to eliminate a large chunk of the search space with every guess. Yes, so Dev has a nice name over here. Dev is saying that we can call this staircase search, right? And yes, Tushar also points out one thing. So Tushar says that this has already been discussed in a previous class. So yes, it has been discussed in the array class. However, it is important enough to bring up again in the binary search class, right? Just to stress the point that binary search is not just always about binary search, right? You can still do sort of a binary search on even though you're not splitting the data into half, right? So very quickly, how can we do the search now? Suppose that we start from the top right. So once again, let us assume that the key we are looking for is 29. We are looking for the value 29, and 29 happens to be over here, right? So we better reach this point. But for now, we don't know where the key is. So let us start from the top right. And we will compare 29 with 50. 29 happens to be less than 50. Since 29 is less than 50, what can I eliminate? What part of my matrix can I eliminate? So where can 29 definitely not lie because of this comparison that I have just made? I know that in this particular column is sorted, right? So over here, in all this column, every element is greater than 50, is greater than equal to 50. And we already know that 29 is less than 50. So my key cannot be in this column, right? My key cannot be in this column. So I can eliminate this column. Do you agree? Yes. All right. Once I have eliminated the column, now I have a different matrix, right? The matrix exists only up till this column, right? So what is the top right part now? What is the top right part of the matrix? It is this particular cell. All right, let us compare once again. So we know that 29 is again less than 40. So once again, by the same argument, since this column is sorted, then 29 cannot be in any of these elements because we know that 29 is less than 40. So let us very quickly eliminate this column as well. Perfect. Let us move on to the next top right element. So this is 30. 29 is still less than 30. By the same argument, we will be able to eliminate this particular column. Does that make sense? Yes. Let us continue. So now the top right element is 20. Right? 29 versus 20. What is it? So 29 is greater than 20. Well, now a different argument appears. Let us look at the different argument. So we know that 29 is greater than 20. Right? So if we look at this particular column, if you look at this particular row, we know that everything to the left of 20, everything to the left of 20 over here, in that same row, right, that has to be less than 20. Everything to the left of 20 has to be less than 20 because the row is sorted. So 29 cannot be over here. So what we can now do is we can eliminate this particular row. We can eliminate this particular row. And notice that these columns have already been eliminated. Right? We move on to the next top right element. So 25 is the next top right element. We compare once again. 29 happens to be greater than 25. So by the same argument, we can eliminate this row. Then we move to the next top right element, which is 29. And now we can return yes, we have found 29 and 29 exists in our matrix. Is that clear? Yes. So we are not doing binary search. We are kind of doing a staircase search, right? We are zigzagging around. So in this particular case, we moved along this path. There's nothing binary about this, but this is still an example of binary search. Is that clear? Cool. Now, very quickly, what will be the time complexity? Time complexity of this approach. So we have already seen that linear search takes this much time. Binary search will take either n log n time or m log n time. What about this particular approach? Well, for this approach, we have to go from the top right corner, in the worst case, to the bottom left corner. Right? From the top right corner to the bottom left corner. And the path does not matter. The path does not really matter because in both the cases, we will be covering n different rows and m different columns. Right? So our total path length is equal to n plus m, irrespective of what paths we take. Right? Either we go this way, or we directly go over here, or we maybe take this weird way. Right? All these cases have the same path length of n cross m, m plus n. So the time complexity will be order of n plus m. Is that clear? So this was a repeated question, but this was still very simple and very relevant to binary search. Let us move on now. So we very quickly saw this question. Let us move on to the next question. So Animesh over here says, can we rewrite this? So Animesh says that, okay, perhaps we can also rewrite this as order of max of n comma m. And that is true. That is true. So as we saw in the very first class on time complexity analysis, we saw that we can rewrite this part as max of n comma m, right? Because asymptotically, these complexities will turn out to be the same. They are related by a constant factor of each other. All right. Perfect. Moving on, let us see a more challenging question. So this question is very famously called aggressive curves. Aggressive curves. I think this question was originally from the platform Spodge, right? And this question is very, very common. I mean, this question happens to be one of the favorites for all the companies. So this question has been asked numerous times at Google. This question is still asked very frequently at places like DirectTime and Amazon. And this is a very, very nice question, right? The special thing about this question, as you will see, is that it has a very nice solution using dynamic programming as well. But it can also be solved using binary search, right? So a lot of the times when a student goes to an interview, they are expecting a difficult interview question, right? A lot of the students are afraid of dynamic programming, even though dynamic programming is pretty easy, right? So whenever they see this question, the natural approach, the natural idea that comes to their mind is, okay, I can try dynamic programming on this particular question. I mean, of course, dynamic programming solves this question, but binary search solves this in a faster manner. Okay, so let us quickly see the question. The question goes something like this, that you have n different stalls. You have n different stalls, right? And the stalls, so let us say n is greater than 2. You have n different stalls. So you have more than 2 stalls. And you have C cows, right? Once again, C is going to be greater than 2. There's one constraint over here, that C is less than or equal to n. All right? We have n different stalls and we have C different cows. Now, you have been given the location of these stalls. The location of these stalls has been given to you. So let us say that we have 4 stalls, right? N equals to 4. And the location of these stalls are 1, 2, 5, and 8. All right? Or let us say make this n equals to 5. Let us just add one more. And 1 to 5, 7, and 8. What that means is that the first stall, the 0th stall, is at location 1. The first stall is at location 2. The second stall is at location 5. Third stall at location 7. And fourth stall at location 8. Right? So you can try to imagine this, that this is one stall, this is the other stall, this is the third stall, this is the fourth stall, and this is the fifth stall. And if this is at 0 meters, then perhaps this stall is at 2 meters, then this stall is at 5 meters. Right? This stall happens to be at 7 meters, and this stall happens to be at 8 meters. So they are unevenly spaced. Right? These stalls are unevenly spaced. Now we also have C cows. Right? Suppose for this example, we have 3 cows. Right? C equals to 3. So now our task is to place these cows. Our task is to place these cows into the stalls. And one cow can only go in one stall. So I'll just draw the cow as a circle. Right? Cows are not sphericals. So, I mean, if you were a physicist, then you would say that, okay, cow is you would consider a spherical cow in vacuum. Right? But we are not physicists over here. So let us just consider this cow in this particular stall. Right? So I can put this cow in stall in many different ways. If I have 3 cows and I have 5 stalls, if I have 5 stalls and I have 3 cows, then very quickly, can someone tell me what is the total number of ways I can put them? What is the total number of ways I can take 3 cows and put them in 5 stalls? Well, that will simply be 5 choose 3. Right? I have to choose 3 stalls out of 5 stalls to put the cows in. And oops. So let us go back. Sorry about that. Right? And if the cows are distinguishable, then I will also have a 3 factorial factor coming. Right? That depends on whether the cows are distinguishable or not. Right? Perfect. So suppose I put the first cow over here in this stall. I put the second cow over here in this stall. And I put the third cow over here in this stall. Right? Now, the cows are aggressive. They want to fight with each other. Right? So we want to maximize the distance between the cows. Right? Now, but there are multiple differences, right? So there's one distance between this cow and this cow, and there's one distance between this cow and this cow. So which distance are we trying to minimize? We are trying to maximize the minimum distance between any 2 cows. Right? So let us suppose that this distance is 6, and this, so let us not suppose that this is 6. Let us just calculate. So this is at 2 meters, and this is at 7 meters. So this distance will be 5 meters. Right? Similarly, this is at 7 meters, this is at 8 meters. So this distance is 1 meter. Right? Now the minimum distance among these two is 1 meter out of 5, and 1 is minimum. So we are saying that this is the minimum distance between 2 cows in this particular arrangement. We want to maximize this distance. We want to place the cows as far apart as possible. All right? And this distance, mind you, this distance is not in terms of the stall number. This distance is in terms of the location of the stall. Right? So we have 2 things over here. We have the 0th, 1st, 2nd, 3rd, 4th stall. We have the stall number. That is not what we're talking about. We're talking about the distance in terms of the location of the stall. Is the question clear? Yes. So very quickly, what do you think should the answer for this particular case be? Suppose that this is the arrangement. I have stalls at 0 meters, 2 meters, 5 meters, 7 meters, and 8 meters. And I have 3 cows. then where should I put these cows? Where should I ideally put these cows to maximize the distance? Yes, the first cow should go in this particular stall. The first cow should go in this particular stall. All right. Then I can put the second cow in this stall, and I can put the third cow in this stall. Is that clear? Yes. So this will be the ideal case. And what will be the final distance? The distance will be, so the distance between these two cows happens to be 5 meters. The distance between these two cows happens to be 3 meters. Right? And the minimum of those distances is 3 meters. So we are making sure that the cows are 3 meters apart from each other. Any pair of cows is 3 meters apart from each other. All right? Perfect. So now the question is that given you have been given N, you have been given C, and you have been given the location of these N stalls. Right? And you have to tell me what minimum distance can you achieve by placing the cows as far apart as possible in the different stalls. I hope the question is clear. So basically, if this is the input, you have to give me the output 3 meters. Right? You have to give me the output 3. All right. Now, how will we do this? How can we do this? So once again, let us start with a very, very brute force approach. The brute force approach would be to try all possible arrangements of the cows. Right? Try all possible arrangements. So as we just saw, so are the cows distinguishable in this particular case? Does it really matter what the first cow, second cow, and third cow is? No, it does not, right? All that matters is what stalls they are in. So over here, how many possibilities do we have? We have 5C3 possibilities, right? Or basically, we have N choose C possibilities, where N is the number of stalls and C is the number of cows. So if we do this brute force, we will check each of the possibilities, and then for each possibility, we will find the minimum distance. Right? We will find the minimum distance. So what will be the overall time complexity of this brute force approach? It will be order of N choose C times. So once we have chosen an arrangement, we still have to calculate. So let us say that we have several stalls and we have chosen to put one cow here, and one cow here. That is not done, right? We still have to measure these distances and find the minimum distance between any pair of cows. So that will take us an additional of order of N time, because we have to go through every pair of cows, right? The total time complexity will be N choose C times N. Well, how big is N choose C? Can someone tell me how big N choose C is in terms of ON complexity? So what polynomial, N to the power what will it approximately be? This is the same as N to the power C, right? N choose C is the same order as N to the power C. Yes, no? Yes, no? Well, not really. Not really, because binomials flip. From the midpoint, the binomials flip. Right? So we are assuming, so this is if C is less than N by 2. Right? C is less than N by 2. So we can rewrite this as, so let us not write this complex expression. Let us just keep this as N choose C times N. And this is in the worst case. In the worst case, this is equal to order of N to the power C times N. Right? Now, if C is very big, if the number of cows is very big, this complexity is perhaps not that big. Right? If there are 10 cows, then you will have to spend N to the power 10 times. That is very, very bad. Right? So let us try to optimize this approach further. Let us try to optimize this. Okay. So those of you who are familiar with dynamic programming, what would you try to do over here? What would you try to do over here? So anyone who is familiar with dynamic programming would say this, that all right, I have several stalls and I have some cows. Right? I have several stalls and I have some cows. That is simple, right? For every stall, I have to make a yes/no decision. I have to make a yes/no decision whether to put this cow in there or whether to not put this cow in there. Right? So people would try to apply DP over here and say that, okay, for the first stall, I can choose whether I'm going to put the cow in or I'm not going to put the cow in. Again, for the second stall, I'm going to choose whether to put the cow in or to not put the cow in. Right? and so on and so forth. I will build my choices, and by DP, I can finally find the answer. Well, that is perfectly valid. Right? That is perfectly valid. And if you do that, your complexity will turn out to be order of n square, which is not bad, right? Which is definitely better than order of n to the power c times n, right? But we can do better. But we can do better. So the moral of this story is that even if you have come up with a solution, it is still worth checking if the solution can be optimized or not. All right. Now let us dive into the most optimized approach, which will be using binary search. Binary search. Perfect. So if we are supposed to use binary search, we have to have a search space. We have to have a search space. We basically have to decide what we are searching for. What are we really searching for over here? Can we search for the location of stalls? Can we search for the location of stalls? That doesn't really make sense, right? Because we have to consider multiple stalls and there are multiple cows. So how it doesn't really make sense to search for the location of a particular stall. What we can search for is the answer itself. We can search for the answer itself, right? So what is the answer over here? The answer is the minimum distance. The answer is the minimum distance, and we are trying to maximize this particular answer. Minimum distance between any two cows. Between two cows. All right. So now that we have figured out what we have to search over, let us quickly discuss the bounds. Let us quickly discuss how large this search space is. So what is the minimum value for this minimum distance? What is the least possible distance that we can achieve? What is the least possible distance when we can achieve? Well, if every stall, if we are forced to put one cow in every stall, and every stall is 1 meter apart, right? So they're just next to each other. They're just next to each other. Then the minimum distance will be just 1. Do you agree? Can the minimum distance be 0? Can the minimum distance be 0? Not really, right? Not really. What is the maximum possible distance that we can achieve? What is the maximum possible distance that we can achieve? Well, this is my first stall, right? This is my 0th stall is at location 0. All right. And let us say my nth stall, my n-1th stall, right? Let us say it is at location, let us say L. All right. And I have to place C cows. I have to place C different cows within this distance. So in the worst case, I mean, even in the best case, doesn't matter how the stalls are arranged. Can I achieve, what is the best distance that I can achieve? If all the stalls are equidistant from each other, then I can simply place the cows one in each of them, right? And then basically my distance will be L by C, right? This is the maximum possible distance I can achieve. Can I achieve more than that? Can I possibly get more than that? No, because once I have placed the cows at equidistant locations, if I try to move any cow to the left or right, then the distance between the previous cow or the next cow, this decreases. Right? And we are supposed to consider the minimum distance between any pair of cows. Right? Minimum distance between any pair of cows. So the maximum possible distance that we can achieve possibly is L by C. Right? And what is L over here? L is simply the maximum of the array. Right? So let us consider that these distances are given to us in the array. Right? So this location of the stalls, this has been given to us in array of size n. Right? So this is simply max of A, right? Max of AL for all n. So we now have the bound. We now know that we are supposed to look for a value in this search space. This search space goes from 1 all the way till max of A of I. All right. Now, what else is required for a binary search? So now that I have a low and a high, I will calculate a mid, and this mid is going to be my guess. Okay? This mid is going to be my guess. Now I have to check. Several things. I have to check, is the guess perfect? Is the guess valid? And is this the correct answer? That's one thing I have to check. Or I have to check, is the guess Is the guess too low? Or I have to check, is the guess too high? Because only if I know all these three things, only if I know the answer to these three things, only then can I adjust my search space. Do we agree? Yes, exactly. We need a proposition. Right? If I don't have these three values, I will not be able to figure out in which direction should I move in the search space. All right. So let us quickly look at how we will do that. So suppose that I tell you, suppose that you have been given this array A of n, size n, and this is the location of stalls. Location of stalls. And I am telling you that, okay, you can achieve a distance. You can achieve a distance of, let us say, 5 meters. Right? We have to verify whether this is true or not. So how will we verify that? How can we verify that? Well, this is very simple. Right? This is very simple. What we can do is, so let us suppose that these are the stalls. Right? And let us suppose that this is at location 0, this is at location 5, this is at location 7, location 11, location 16, location 23. Let us suppose this is how the stalls look. So what we can do is we can place the first cow in here. Right? We can always place the first cow in the first stall. Then we can move on to the next stall and we can check what is the current distance. What is the current distance? Is that distance greater than or equal to 5? Yes, it is, right? So we can safely place the next cow over here because we are trying to achieve a distance of at least 5. We're trying to achieve a distance of at least 5. All right, then we can move on. So when we want to put the third cow, we will come to the next stall and check. Is the distance from the previous cow greater than or equal to 5? So is 7 minus 5 greater than or equal to 5? No, it is not. Right? So we cannot, if we have placed the cow in this stall and we are trying to achieve a distance of 5 meters, then we cannot put the next cow in this stall. All right. What about the next stall? Well, the distance from 5 till 11 is 6. So we can safely place the next cow over here. Does that make sense? Moving on. So we can definitely place the next cow over here. And we can also place the next cow over here. Right? So we can place the cows in this particular manner. Now, if we are able to place all the cows, successfully, right? So remember that we have C cows, right? If we are able to place all the C cows successfully, then what can we say about this particular guess? What can we say about this particular guess? Is this the correct guess? Not necessarily, right? This is a valid guess. This is a valid guess, but we are supposed to maximize this guess, right? So this is a valid guess, but this might not be the maximum value. So we have to continue searching. We have to continue searching with larger values. Right? We have to continue searching with larger values. Suppose that we were not, so if we were able to place it, then we have a valid distance, but the distance can be higher. All right. What is the other possibility? The other possibility is we were not able to place all the cows. Right? For example, suppose over here, let us suppose that my guess distance was, so let me just erase this. So let us say that my guess was that, okay, I can achieve a distance of 10 meters, right? And let us suppose that I had 3 cows to put. So I will try to put the first cow in this first stall. Then I cannot put the second cow in the second stall or in the third stall. I will have to put the second cow over here. Right? I will have to, in this case it will work. So let us just say that we had 4 cows. Let us say that we had 4 cows. So I will put the second cow in this stall. Then I can't put the third cow here. I can put the third cow here. So I will put the third cow over here. Now where do I put this fourth cow? I cannot possibly put the fourth cow because I have exhausted all my stalls. Right? So in this case, we see that we had a guess of 10 meters distance and we tried to place the 4 cows, but we were not able to place all the 4 cows. We were only able to place 3 cows. So that means that my guess is incorrect. Right? That means that my guess is incorrect. Is there anything else that I know? I know that my guess is too high. Right? If 10 meters did not work, then 12 meters or 20 meters or 50 meters will also not work. Right? My guess is too high. I have to reduce my guess. Does that make sense, guys? Yes? So what we are essentially doing is, we are saying that let us initialize the low as 1, the high as L by C. So this is maximum of A of I, right? So maximum of A of A is just the last location, the location of the last one, A of A dot length or N minus 1, right? A of N minus 1 by the number of cows, C. Then while our low is less than equal to high, right? What we will do is we will calculate a mid. So our guess is the mid, which is simply low plus high minus low by 2. Do you agree? Now we have to verify the guess, right? So if works, right, if this array for this number of cows, for this value, for this guess, if this works, so we will write this function works. But if this works, then what can we say? If this particular thing works, then what can we say? We can say that, hey, this guess is valid, but it might be too low. Right? This guess is valid, but we could do better. Right? So we have to increase. We have to increase our guess. Right? How will we increase our guess? We will say low equals to mid plus 1. Right? But this guess worked. Right? This guess worked, so we must also save it. This was the largest guess that worked. So let me also save a variable over here, largest working guess. Right? Let me save a variable over here, largest working guess. And this was initialized with, let's say, 0 or minus infinity, whatever you want. And I can say over here that largest working guess equals to maximum of my guess, my mid. So it is maximum of mid, the current guess, comma the largest working guess. All right, I can make sure that whenever I have a valid guess, I save the largest of those valid guesses. Is that clear? On the other hand, if this does not work, then I have to adjust my high. High equals to mid minus 1. Right? And at the end of this loop, when this loop is through, I can simply return whatever maximum guess I have found so far. So largest working guess. Does that make sense, guys? Does this binary search make sense? Yes? We still have to write this function, right? We still have to write this works function. Well, this function is very simple, as we saw. How will this function work? So we have to write works. This will take an array. This will take the number of cows. This will take the number of cows, and it will take a guess. So what will we do? We will start from the location first. Right? We will say that the previous stall equals to 0. Right? We will place the first cow at location 0. Now, how many cows do we have to place now? So for I goes from 1 till C minus 1. Right? We have already placed the 0th cow. Now we have C minus 1 cows remaining to place. Right? So we will go over each cow, and then what will we do? Right? We will try to place the cow in the next stall. So we will also let me also save a stall number over here. Right? So stall number is 1. Right? I have already used up the stall number 0. So the current stall number is 1. Okay. So now what can I do is I can try to put the cow in over there. So I can say while the location of the current stall, right? While A of stall minus A of previous stall. Right? If this distance, while this distance is less than my guess, I cannot really put this cow in the current stall. Right? So I must move on to the next stall plus plus. Do you guys agree? While this is true, I will do stall plus plus. Right? And finally, I will say that, all right, once I have this, I will say previous stall equals to stall. Right? So I will put the cow in there. So this is my loop. Now, of course, this loop might not always work. Right? Basically, when will it fail? When my stall number has become equal to the size of the array when I have reached the last stall, but my cows have still not been finished. Right? My cows have still not been finished. So I can put a condition over here. I can very quickly check over here. So instead of directly doing this stall plus plus, let me do a stall plus plus. And now I can check if stall equals to n. If I have already reached the last stall, then I can return false. Return false. Because this guess did not work. I still have some cows to place, but I have exhausted my stalls. Right? So I will return false that, hey, this guess does not work. If I can complete this for loop, that means that I was able to place all the C different cows. I was able to successfully place all the C different cows at a minimum distance of guess. So over here, I can return true. Return true. Does that make sense? Does this function, this works function make sense? Yes? Do you guys agree? Perfect. So what will be the time complexity of this? What will be the time complexity of this entire code? Well, let us take it step by step. Right? How much time does the works function take? Given a particular guess, how much time does it take to verify that guess? Well, we have to linearly search through the array of stalls. Right? We have to linearly check the array of stalls. So this works takes order of n time, right? Where n is the number of stalls. Do you agree? Do you guys agree? So, okay, some people will over here say that, okay, you have a while loop. You have a while loop over here, and you have a loop that goes C times over here. So isn't the complexity going to be C times n? Shouldn't the complexity be C times n? Well, no, right? The complexity of this entire for loop is not C times n, because as we see, this variable stall is strictly increasing. Right? This variable stall is never reset. So it can only increase. And the maximum possible value of stall can be up to n. Right? So it is the complexity of this entire nested loop. It is not C times n. It is simply order of n. Is that clear? Yes, perfect. What about this? What about this binary search? So I think I deleted something from here. Right? What about this binary search? So this binary search takes us how much time? It takes us log of the size of search space. What is the size of search space over here? Is the size of search space n? No. The size of search space is this value over here. Right? This is the size of search space. A of n minus 1 by C. Right? This is the size of search space. So this will be the number of times we will have to do the binary search. And each binary search will take us order of n time. So we can say that the complexity of this is order of log of max of AI, max of AI, so the maximum stall location divided by the number of cows, right? The log of that times n. Is that clear? Yes? Yes or no? Well, C over here. Is that clear, guys? So C is not a constant, so we can't really ignore it. So this will be the final value. This will be the final value. And is this better than n square? So do you guys think that this is better than n square? Well, that will depend. That will depend on how large this A of I is. Right? How large this A of I is. Is that clear? So it might be the case that A of I is 1 trillion. If A of I is a very, very large number, then it might make sense. It might make sense to do this n square solution. But that is going to be extremely, extremely rare. Right? So if n is large, then definitely this log value will be much, much smaller. Right? So in general, this approach will work faster. Is it clear? So we saw the brute force approach for this. Right? That was order of n to the power c plus 1. Right? Then we saw the DP approach for this. We did not discuss this in detail. We will discuss this maybe later. So this was order of n square. And then we discussed the binary search approach. And this turned out to be order of log of max of A by C times n. Is that clear? Yes? Any doubts on this particular question? I hope that you will be able to code it. So this is part of the assignments. So please try and code it. You will actually learn a lot when you implement these solutions. Right? And one more thing, please try to make sure that you make the code modular. Right? So just like we have discussed in the class, please define a separate function, right, that will check the guess. You can also write this. You can also write this code over here as well. Right? You can also write this code over here as well. But please do not do that, right? Because then your logic will not be clear. You will be mixing the logic of your binary search with the logic of your checking a guess. Let us keep those two logics separate. Binary search is separate. Checking if a particular guess works or not, that is separate. So please let us do the separation of concerns thing and then keep them in different functions. All right. So let us move on to another question. So this is again fairly challenging question, and this is also a very, very interesting question. Okay. So the question goes something like this: that you have been given an n. You have been given a number n. And this n is a 64-bit number, 64-bit integer. And let us say it is also positive. All right, let us say it is also positive. Let us also say that n is greater than 2. All right, let us also say that n is greater than 2. So basically, what values can n take? So n can take a value from, let us say, suppose 3, all the way to 10 to the power 18, perhaps. Right? N can take all these different values. Cool. So now what we are saying is, let us suppose that n written in some base k. N written in some base k. So k can be either 2, in which case we are writing n as a binary number, right? Or k can be ternary, or k can be 3, or k can be 8, in which case we are writing n as an octal number, right? But if we write k in, if we have n in some base k, and if this equals to 1, 1, 1, 1, 1, dot, 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 right? If this is just a string of ones, right? Then we will say that, okay, this k is a good base. Good base. All right? Is that clear? For example, let us say that n equals to 7. All right? N equals to 7. Then what different bases will work? What all different bases can work? So first of all, this k equals to 1 will always work. Right? Yes or no? I can always write something in base 1. Right? A number n in base 1 is just 1, 1, 1, 1, 1 n times. Do you guys agree? Yes? Let us not do that. Let us not do that. Let us ignore this k equals to 1 thing. All right? Let us ignore this k equals to 1 thing. So we are also considering that k is greater than 1. That k is greater than 1. Okay. Now let us try some other base. So 7 written in base 2. What does this look like? What does 7 in base 2 look like? 7 in base 2 is, so this is base 10, my bad. This is base 10. In base 2, if I write it, then it will be 1, 1, 1. Right? So 2 is a good base. 2 is a good base for 7. All right? Are there any other good bases? Are there any other good bases? Yes, no? Well, what happens if we write 7 in base? What happens if we write 7 in base 3? What do we get? So we get 1, then 4 remains, right? Then we will get, so just give me a second. So the last, so 7 is basically equal to 3 to the power 0 plus 3 to the power 1 plus 3 to the power 2. So this is going to be 3 to the power 3. Yes, so this is going to be 2 times 3 to the power 1 plus 1 times 3 to the power 0. Yes, so this is 7. This is 7. So what will 7 look like in base 3? What will 7 look like in base 3? 7 will look like 2, 1 in base 3. Right? 7 is 2, 1 in base 3. So is this a string of ones? Is this a string of ones? No, this is not a string of ones. So 3 is not a good base. 3 is not a good base. All right, let us continue. Let us continue. So we can check the base 4, we can check the base 5. That is also not going to work. There is some other base that is going to work. It's 7 in base 7 is also equal to In base 6, this is going to be equal to 1, 1. Right? In base 6, this is also going to be equal to 1, 1. Do you guys agree? Yes? In fact, if I have any n in base 10, then this is equal to 1, 1 in base n minus 1. Yes or no? 1, 1 in base n minus 1, that is simply n. Why is that? Because see, 1, 1 in base n minus 1, this is equal to n minus 1 to the power 0 times 1 plus n minus 1 to the power 1 times 1. Right? And that is equal to what? N minus 1 plus 1, which is just n. Right? So any number n that I have, I can always write in one less base and get a string of ones. So 7 equals to 1, 1 in base 6. Right? 13 equals to 1, 1 in base 12, and so on. Do you guys agree? So n minus 1 is always a good base. Right? N minus 1 is always a valid base. So this is also a good base. Right? Good. Now the question once again is that you have been given a value of n, right, such that n is greater than equal to 3 and n is less than or equal to 10 to the power 18, suppose. So it is a 64-bit integer, positive integer. We have to find the smallest good base. All right, so we found several different good bases, right? For 7, we found that 2 works. So we found that 2 works, 3 does not work, 4 does not work, 5 does not work, 6 works. Right? That is what we found for 7. So what will be the smallest good base for 7? What will be the smallest good base for 7? It will be 2. Right? It will be 2. So smallest good base. So for example, if n equals to 7, then the answer will be 2. And why 2? Why not 1? Because 1 works for everything. Right? If we allow 1, then for every number the answer will just be 1. Because base 1 works for everything. Is that clear? So we are saying that the smallest good base, let us call this k, is greater than or equal to 2. So this is the question. I hope the question is clear. Given an integer n, return the smallest good base. For example, if your value is 7, then you are supposed to return the value 2. All right. So what can our approach be over here? What can our approach be over here? Let us start with the most brute force approach. Brute force approach. What will the brute force approach look like? In the brute force approach, we can simply check all the possible options. Right? We can simply check all the possible options. So we can go from base k equals to 2 all the way till n minus 1. Right? We can check all these different values. Now, once we have a base, we have to convert n into that base, right? Base k, and check if this is a string of ones. If this is a string of ones, well, how much time does it take to convert a number into base k? How much time does it take to convert a number into base k? Can someone quickly tell me that? It will take me log of n time base k. It will take me log n time with a base k. This is how much time it will take me to convert a number. Why? Because I have to repeatedly divide that number by k. Right? I will say that, okay, the last digit equals to n mod k. Then I will divide the number. Right? I will say n by equals to k. N by equals to k. This is not or this is a simple division. Right? Then I will say d1 equals to once again n mod k. And then I will again say n equals to n by k. Right? And this will be in a loop. This will basically be in a loop. That is how I convert the base. So it will take me log of n time base k. All right. So what is the total time complexity over here? I have these many bases to check. And it takes this much time to check each base. So it will be order of n times log n. Right. So my brute force approach takes me order of n times log n time. Is that clear? Yes. Now this is not very good, right? This is not very good. If my n is, let us say, 10 to the power 18, then it will take me 10 to the power 18 steps. That is definitely not possible. I cannot do 10 to the power 18 steps on any computer. Yes? So we should better come up with a faster solution. We should try to come up with a faster solution. Okay. So what can we do over here? What is the first thing that comes to your mind? What is the first thing that comes to your mind? The first thing, since we have been doing binary search, might be that, okay, let me make a guess. Let me guess base B. Let me guess base B and check if the guess is valid or not. Yes, that is what comes to your mind. That let us take a base B, let us consider a random base B, and let us check if it is valid or not. Well, this is not going to work for this case. This is not going to work for this case. Why? Suppose that my number was 7. I checked the base 2. I checked the base 2 and it worked. What does that tell me? Does that really tell me anything? That tells me that 2 works. That tells me that 2 works, but that is not enough, right? I also have to understand. Is my guess too low or is my guess too high? Yes. Just because 2 works, that does not mean that my guess is too low or that my guess is too high. Do you agree? It might be the case that 7 of 6 still works, right? So for the base 7, 7 of 2 works, 7 of 3 does not work, 7 of 4 does not work, 7 of 5 does not work, 7 of 6 works. This works. So suppose you make a guess. There is a valid value to the right of it as well as to the left of it, and you do not know in which direction you have to go. So if it turns out to be false, if you figure out that, okay, the guess did not work. So are you supposed to increase the base or are you supposed to decrease the base? Are you supposed to increase the low or are you supposed to decrease the high? Does that make sense? We have no way of knowing in which direction should we move our guess. So we cannot do the binary search over base. Does that make sense? Because once again, if we go back to the first class, if this is our search space, then we need to come up with a proposition such that all the answers here are yeses and all the answers here are no's, so that we can binary search for this midpoint. For this particular thing, the answer over here is yes, the answer over here is yes, the answer over here is yes, but all the other numbers can be no. Right? We don't really know. It can be randomly. It can be in a random manner. So binary search is not going to work for this proposition. Is that clear? Yes, it seems very, very seductive to try to apply binary search over here. I have a base. I can verify if it is a valid base or not. So let me just binary search over the base. That is not going to work, unfortunately. So what else can we do? So we have to look at the question from a different perspective over here. So let us suppose that we are talking in base B. Right? Suppose we are talking about in base K. Suppose base K. Right? Then if basically my number n in base K is a string of ones, I already know what the string of ones is, right? I can construct this string of ones, right? I know that this is in base K. I know that this is a string of ones. The only thing I don't know is how many ones there are over here. Yes, how many ones there are over here. Let us call this value I. Does that make sense? So n written in base 2 will have 3 ones. Right? N written in base 6 will have 2 ones. Right? So instead of trying to binary search over the value of k, let me try to binary search over the value of I. Okay? But let me first establish a relation between these two. So if n in base k is a string of ones in base k, so n is equal to a string of ones in base k, right? And let us say that there are I ones over here. Then what can I say? Is there any relationship between n and k? Yes, there is, right? What is the relationship? I know that 1 times k to the power 0 plus 1 times k to the power 1 plus 1 times k to the power 2 plus all the way till 1 times k to the power I, right? This thing equals to n. Right? If I have this number in base k, then this is the expansion of it, and I know that this must be equal to n. Right? What can I say? N equals to summation of k to the power I for k to the power, let's say, x, for x equals to 0 till I. Right? So this is what is this? This is a geometric progression. This is a GP. So can I write the sum of it? The sum of it is simply k to the power I plus 1 minus 1 by what? By k minus 1, right? So the sum of a GP, summation of r to the power I for I equals to 0 till k, this is equal to what? 0 till n, this is equal to r to the power n plus 1 minus r to the power 0 by r minus 1, right? Yes. So just notice that there is this denominator over here, right? You can't simply say that the denominator is 1, right, Shazia? So Shazia, there's a small mistake in your formula. You have to make sure that this denominator is also dependent on k. Right? So we can say that n equals to k to the power I plus 1 minus 1 by k minus 1. This is the relation that we have established between n, k, and I. Now I know that I cannot really binary search over k, but that's okay. Let me binary search over I. Right? Let me binary search over the value of I. All right. Now let us suppose that I have I ones over here. Right? Let us say that I have I ones over here. Right? And this is equal to n. Right? This is equal to n. Then what if I'm trying to minimize? So remember that I have to find the smallest good base. Right? I'm trying to minimize the value of k. So what am I trying to do with the value of I? If see n is my constant, right? N is my constant. I'm trying to minimize the value of k. So what am I doing with I? I'm trying to maximize the value of I. Right? I'm trying to maximize the value of I. Do you agree? Yes or no? Right? Yes or no, guys? So that is one thing we know. Perfect. We know that we are trying to maximize the value of I. All right. Let us also consider what is the search space of I. Search space of I. What is the search space of I? So I can be, so this can be, so let us suppose that I write n in base 2, right? This is the smallest base that I can possibly have. So that will give me the largest possible string of ones. How many ones will I get when I write n in base 2? I know that n is a 64-bit integer. Right? So the maximum search space, the maximum value of I can be 64. Right? So I can have all the way from 2 all the way to 64 ones in my string. All right. Now, once again, the problem over here arises. If I know that this sequence of I works, does that tell me anything about this sequence of I or about this sequence of I? Does that tell me anything about this sequence of I or this sequence of I? It does not. Right? I know that I have to maximize the number of ones. But if this works or if this does not work, it doesn't tell me whether I should increase it or decrease it. So I cannot really binary search. Over the value of I either. That's sad. But how many i's can there be? We just established that the maximum possible value of I can be 64. On the other hand, when we were talking about k, we established that the maximum possible value of k can be up to n minus 1. So what would be the other search over? Should we search over k or should we search over I? This can be up till n minus 1. This can only be up till 64. Right? So this is much better, right? Do you guys agree? Searching over I is much better. So I can simply check for every possible I. For I goes from 2 till 64. Let me check for all the possible. Strings of 1. Right? Let me check all the possible strings of 1. Now what I will check? Now I will see whether n can be written in the form of 1 1 1 1 1 I ones to the base k. Right? Whether I will try to see whether any such base k exists that will give me this. Does that make sense? I can go over every I. Yes, but how do I find this k now? I know the relationship between these two, right? I know the relationship between all these numbers. I know that n equals to k to the power I plus 1, right? N equals to k to the power I plus 1 minus 1 by k minus 1. I know this relationship. So now, if I have the value of I and if I have the value of n, can I find the value of k? Can I find the value of k? Yes. How will I find the value of k? That is difficult, right? I will have to manipulate the formula. Right? If I want to find the value of k, I will have to manipulate the formula. I will have to extract k out of it. I will have to extract k out of it. So can someone solve this equation for me very quickly? Can someone solve this equation for me very quickly? Well, you can't really. You can't really do that. Right? Because this k, this I, might be a very, very large number. Right? And you don't, so for higher degree polynomials, you don't always have a way of solving an equation. So you can always solve a quadratic. If you have a quadratic equation, you can always solve it. If you have a cubic equation, you can always solve it. Right? But for higher equations, I'm not sure for the fourth power, but I know that from fifth power and above, right, it is not always solvable. It is not always possible to solve a higher degree polynomial. All right. So this equation might not be solvable. So what can we do? Do we have to give up? No. Here is where we can binary search. We can binary search for the value of k. Right? We can try to plug in the value of k and try to binary search for an answer that works. Is that clear? So what we will do now is we now have to find a k that works. What is the maximum possible value of k? The maximum possible value of k, so the minimum possible value of k is 2. The high maximum possible value is n minus 1. And now I can binary search over this value of k. I just have to find one k that works. I can binary search for k which satisfies this equation, which satisfies the equation n equals to k to the power I plus 1 minus 1 by k minus 1. Is that clear? So just like in the first class, we tried to binary search. So we did not do it in the class, but it was part of your assignment. Right? So in the assignment, you had to do a binary search for the square root of a particular number. Right? For the square root of a particular number. Yes, so n minus 1. Right? This is n minus 1. Right? So we can binary search over the value of k. Is that clear? So how much time will this binary search take? How much time will the binary search for k take? This is my search space. Right? This is my search space. My search space has size of n. And I'm doing a binary search, so it will take me log n time. Log n time to binary search for a value of k. But I have to do this 64 times. I have to do this for all values of I. So this will be times 64. So the overall time complexity of my approach will just be 64 times log base 2 of n, which will just be log n. That is amazing. Right? We went from an n log n solution. We went from an n log n. What happened over here? N log n brute force, and we reduced it down to a constant times log n. Is that clear? Yes. So even though the question does not directly involve binary search, there is still an involvement of binary search. And the moral of this particular question is that be very, very careful. Be very, very careful. For binary search, you just don't have to make and verify a guess. You also have to understand, given the guess, if that guess worked, then is the guess too high or too low? Right? If the guess worked or if it did not work, this is not enough. You also have to establish, is the guess too high or too low? Because if you cannot do that, then you will not be able to binary search for your answer. Is that clear? Perfect. Ankush has asked a very good question. Ankush is saying, how can we know whether binary search will be applicable for this particular question? Now, that is a very, very tricky question. So basically, the most common answer you will find to this is practice. Right? The most common answer that you will find to it is that, okay, if you just practice, then practice will make you perfect. You will get to know which way, which approach you have to apply. But that is not the entire truth. There is a separate way as well. So there's a systematic way. There is a systematic way of approaching problems. Right? Now, unfortunately, I cannot teach this systematic way in a YouTube class. Right? It cannot be taught in a 1-hour class. So the entire scalar curriculum of DSM algorithms is based on tries to teach you this systematic way. Right? So that whenever you get a new problem, you can just apply the systematic algorithm and try to come up with a solution for that. Okay, that is what we teach in the scalar classes. All right. So I mean, we could cover this, but this is going to take a very, very long time. We'll have to take a very long class. We'll have to consider all the DS algo things, and then we will have to tell you the approach. Perfect. So that is it for today's class. Let us end the lecture now, and see you then. So once again, you can find the assignment set in the video description. Please make sure that you attempt the problem set. Okay then. Have a nice day, guys.